Our solar system is vast. From our own star, the Sun, to Earth is nearly 150 million kilometers, or 1 astronomical unit. Jupiter is 5.2 AU distant, and Pluto up to 48 AU. And the solar system extends far beyond this into interstellar space. We humans cannot travel that sort of distance, at least not yet. But we can and do send our robots and probes in our place. And the results are astounding. The ion-propelled Dawn spacecraft is one of our emissaries that has rendezvoused with 2 asteroid belt objects in its multi-year mission.
The Dawn mission is one of NASA's Discovery Program missions that launched in September of 2007. So it's had a long, circuitous journey from the Earth, flying past Mars and out to the asteroid 4 Vesta, where it spent a year orbiting this small rocky object and mapped its surface and determined its bulk composition and geological aspects of Vesta before leaving the gravitational field of Vesta and traveling for another 3 years out to the dwarf planet Ceres.
Before the arrival of the spacecraft Dawn at Ceres, we were expecting an inert rocky body.
Instead, they discovered a world of mystery and surprise. Dawn has been orbiting Ceres for more than 2 years now, providing us with fascinating views of an alien world. The mysterious bright spots on Ceres appear to be salts deposited on the surface by subterranean activity. Support for this theory can be found in another feature of interest, the bright mountain named Ahuna Mons.
Outer space is vast, mysterious, and overwhelming, and in a way, so is the human mind. Just as scientists endeavor to understand the unknown, we can take steps to better understand ourselves. And that's why we're so excited to share the paid partner of today's video, BetterHelp. BetterHelp is an online therapy that connects you with a credentialed professional from the comfort of your own home. No waiting rooms or inconvenient commutes, just support when and where you need it. Seeking therapy can feel like a big step, but it doesn't have to be. Instead of getting stuck in an endless loop questioning yourself, you can talk through your concerns with someone who's trained to help you find real answers, break old patterns, and build a stronger mindset. All you have to do is fill out a quick questionnaire, and BetterHelp will match you with a therapist tailored to your needs. You can message them anytime and schedule live sessions via phone, video, or chat. And if the match isn't quite right, you can switch therapists at no extra cost. And their customer support team is always there to help you if you have any questions. With over 7,000 reviews and a 4.5 rating on Trustpilot, BetterHelp is a platform you can trust. Going to therapy is a sign of strength, not weakness. Click the link in the description or go to betterhelp.com/sparkdocs to start your journey and get 10% off your first month.
We have looking in detail about the shape of the mountain, and we have compared with what we know from volcanic constructs, and we have found that Ahuna Mons' shape is very similar to that of a volcanic dome that is built by very viscose material.
When we saw Ahuna Mons, we saw that its shape was very tall. It was very tall and had steep slopes, and that reminded us of certain places in the solar system, including Earth and Mars, that had domes that were formed by volcanic activity of very slow-moving, thick material. However, on Ceres, the temperatures are so cold that the same type of magma on Earth and Mars just can't exist on Ceres. So we then concluded that the magma, or the material that's flowing on Ceres, had to be composed of mostly very salty water that would flow at the low temperatures of Ceres. And when exposed to the surface, when they were pushed out onto the surface, they would freeze and form this steep-sided dome. Ahuna Mons is unique in the solar system. There's no other place in the solar system that has a structure that matches that of Ahuna Mons, and it has to be formed by cryovolcanic activity.
Scientists at the German Aerospace Center have used stereo images to create a global digital terrain map of the dwarf planet. Another surprise? A study published by lead author Norbert Schorghofer shows permanently shadowed regions at the North Pole. These are expected to be cold enough to accumulate water ice over long time spans. Future spacecraft visiting Ceres are likely to find freshwater ice there.
So right now we are not only learning about dwarf planet Ceres, but also about planets and small bodies in the outer solar system, like Pluto and its moon. And so we are in a phase in space exploration where we are learning about a new class of objects. And we are seeing that these objects are surprising as they have recent features on their surface. These observations tell us Ceres was active in the recent past and might be even active today. And these tell us the importance of sending a spacecraft to a dwarf planet to have a close look at the surface, as we are learning new things that are unexpected.
Dawn is now orbiting only 386 kilometers above Ceres, which is closer than the space station is to Earth. And it will continue to return spectacular views. One of the key technologies that made Dawn such a success was its ion drive.
Ion propulsion allows us to undertake missions which would be impossible without it. There have been previous missions and tests of ion propulsion to validate the basic technology, but Dawn now has made it a reality. Dawn's the only spacecraft ever in more than 58 years of space exploration to orbit 2 extraterrestrial destinations, the last uncharted worlds in the inner solar system. And it not only allows us to get to these distant bodies, but once we're in orbit, we can maneuver extensively in order to get the best possible science that we can from the mission.
Our second deep space emissary has only recently arrived at its destination, the giant planet Jupiter. Juno is our fastest probe to date. Reaching a top speed of 265,000 kilometers an hour, or 73.6 kilometers a second, it has traveled for almost 5 years to reach its target and orbits the poles of the largest planet in the solar system.
Juno's the fastest spacecraft ever to venture into the outer solar system. It's the first to orbit pole to pole about Jupiter, and it's the most heavily shielded spacecraft that we've ever launched. The mission is designed to basically wrap Jupiter in a dense net of observations, completely covering the sphere. So to do that, we need a polar orbit, one that passes over the North Pole, along a line of longitude, and over the South Pole. And we do this over the 37 orbits of the nominal mission, and by the time we're done, we've got orbits separated in longitude by about every 12 degrees. So we completely cover the sphere.
Basically, the interior of Jupiter is nearly unexplored. What we see when we look at Jupiter and all the great, amazing stuff we've discovered about Jupiter is about the moons that orbit the planet. It's about the atmosphere and the enormous weather systems and the great red spot and belts and zones, stripes across the planet, all kinds of really cool, interesting, exciting stuff, but it's kind of skin deep. When we look at Jupiter, we're going, 1% or 2% of the way down into the planet. That's what we're really seeing. Everything else about Jupiter, the deep interior of Jupiter, is nearly completely unknown.
To peer beyond the veil, the suite of instruments on board Juno includes a gravity radio science system, plasma and energetic particle detectors, ultraviolet and infrared spectrometers, and a vector magnetometer.
A magnetometer is, it's best to think of it as a fancy compass. Unlike a compass that just records the direction of the magnetic field, our instrument tells you both what direction the field is in and what the magnitude is. And we can measure that very, very accurately to 100 parts per million. Juno's magnetometer is another in a long line of magnetometers built here at Goddard Space Flight Center, following designs developed by Mario Cunha years ago. Our instrument is between 1 and 2 orders of magnitude more accurate than anything that's flown to Jupiter before. And of course, part of that is the result of the star cameras that we're able to fly with our sensors so that we can determine the absolute orientation in space of these sensors. If we did not know the orientation of the sensor as well as we can determine it with the star cameras, we would lose accuracy in the vector measurement. So we carry 4 star cameras with our 2 magnetometer sensors. These have to be held in the same orientation with respect to each other under very extreme environmental conditions. So we designed what we call a magnetometer optical bench. It's a special structure, about a square foot in size, that is made of a carbon silicon carbide material, almost impossible to machine. But once it's fabricated and the sensors are assembled, they act as one. And that's one of the reasons why we can achieve much higher accuracy than has ever been attempted before.
Studying the magnetosphere of Jupiter is a prime objective.
Magnetic fields have been a curiosity for thousands of years. And so, of course, we know now that magnetic fields are generated by what's called dynamo action, the convective motion of an electrically conducting fluid. Even though we can map the Earth's magnetic field with extraordinary accuracy with satellites in orbit about the Earth, the one thing we can't do is see clearly through all the crustal magnetization that is right beneath our feet. Jupiter is a gaseous planet, hydrogen, helium. There is no magnetized crust that obscures our view of the dynamo deep below. So the exciting part about the Jupiter mission is that we'll be able to image for the first time the magnetic field on the dynamo surface in a way that would never ever be possible on Earth. Jupiter is also the planet with the largest magnetic field. Its magnetosphere is huge. If you were to look up into the night sky, and if you could see the outline of its magnetosphere, which you can't, it would be about the size of the moon in the sky. It's a very, very large magnetosphere. In fact, in the Voyager program, we learned that the magnetic tail, the part of the magnetosphere that is drawn away from the sun, extends all the way out to the orbit of Saturn and in all likelihood beyond. It's a very large feature in our solar system. It's a pity we can't see it.
Of course, a strong magnetic field traps more radiation within its grasp, another issue for Juno.
There's 2 types of radiation we worry about. One is when we fly through the radiation belt, we get an instantaneous exposure, we call that flux. The other is flying through the radiation belt again and again and again gives us something about accumulation, we call that dose. And so in the beginning of the mission, we fly largely close to the planet underneath this kind of flat donut-shaped radiation belt, and then we fly around it. But eventually we fly more and more through the belts, and our radiation levels, every orbit, get worse and worse and worse. We get over 80% of radiation exposure in the last half of the mission.
For me, the great excitement is the opportunity to look down and get the first clear, unobstructed view of what the magnetic field looks like on the surface of a dynamo where it's generated. It's always incredible to be the first person in the world to see anything. We stand to be the first to be able to look down upon the dynamo and see it clearly for the first time.
Our emissary to the ringed planet Saturn is now in its final year of operation. Its outstanding performance has included dropping a probe on the moon Titan, making extensive observations of Saturn and its moons, even adjusting its mission to fly through the water vapor plumes discovered gushing into space from the moon Enceladus.
Cassini was never designed to look for life in the Enceladus ocean. But it does have powerful instruments that can be used to look for habitability. So we're looking for the conditions suitable for life. Now Enceladus is a tiny moon, but it's really intriguing. It's got this plume that is shooting out from its south pole. The plume's mostly comprised of water ice, that gets frozen when it's ejected out into space. Most of these particles are coming from these 4 major fractures that we call tiger stripes. Life needs 3 things, right? It needs water, it needs chemistry, and it needs energy. And right now, some of these lines of evidence are telling us that Enceladus has these 3 things. We see some salts, but most importantly, we see organic molecules, things like methane. We also see CO2, ammonia. One of the things that Cassini can look for is molecular hydrogen. This is the smallest molecule that exists in the universe. It's 2 hydrogens bonded together. This molecule can tell us about things like hydrothermal activity going on in the ocean of Enceladus. And this is very important as we start to answer that ultimate question of, is there really life on Enceladus?
NASA's Cassini mission has begun a daring set of ring-grazing orbits, skimming past the outside edge of Saturn's main rings. Cassini is flying closer to them than it has since its arrival over 12 years ago. It will begin the closest study of the rings and offer unprecedented views of moons orbiting near them. Even more dramatic orbits will take Cassini through the F ring, the outer and most active ring, which contains 1 ring and a spiral strand around it. Cassini will make its final orbit later this year and plunge into the Saturnian atmosphere, ending more than 11 years of scientific observations. Traveling over 10 years and 5.5 billion kilometers, New Horizons is our emissary to the outskirts of the solar system. In a dramatic flyby, New Horizons scanned Pluto and its main moon Charon. The brief encounter amassed gigabytes of data, which the spacecraft took months to download to Earth. Its close-up details of Pluto's terrain generated a great many questions. It looks more complex and highly active geologically than first thought, with solid nitrogen ice forming many fascinating and colourful textures and landscapes. New Horizons captured this high-resolution enhanced colour view of Charon just before closest approach. Charon's colour palette is not as diverse as Pluto's. Most striking is the reddish North Polar region, informally named Maunder Macula. After such a successful flyby, the mission has extended to include a second Kuiper Belt encounter. New Horizons is set to fly past 2014 MU-69, a Kuiper Belt object currently about 1.6 billion kilometers beyond Pluto. Arrival time, January 2019. As one mission ends, another is about to begin. Bepi Colombo, Europe's first mission to Mercury, is currently being put through its paces at ESA's European Space Research and Technology Centre in the Netherlands. Bepi Colombo consists of several components in a so-called spacecraft stack. Apart from the two orbiters, there's also the Mercury transfer module, which contains the solar electric propulsion engine to get them there.
Okay, what we have here is the MTM, the Mercury transfer module, which brings us, or our two spacecraft, to Mercury, the 3 xenon tanks and the 4 thrusters. And when we arrive at Mercury, this unit will be jettisoned, and then we only have our 2 spacecraft.
The 2 spacecraft are ESA's Bepi Colombo and the JAXA magnetospheric orbiter. Mercury is the closest planet to the Sun in our solar system. Yet despite temperatures reaching around 500 degrees Celsius, the previous NASA Messenger mission found evidence for ice at the planet's north pole.
One spacecraft is provided by ESA, which is MPO, we call it MPO, Mercury Planetary Orbiter. And this spacecraft has a focus more on the planet. We want to observe the planet, do remote sensing, characterize the surface, count the craters, wanting to know about the composition of the surface, the interior of that planet. And in addition, we have a second spacecraft, and this spacecraft is called the Mercury Magnetospheric Orbiter, more focused on the environment, and this spacecraft is provided by the Japanese Space Agency.
The Messenger mission found other surprises at the smallest planet in our solar system. It discovered more chemical elements and compounds with small boiling points, known as volatiles, than expected at the surface. Messenger focused on the north polar region, whereas Bepi Colombo and its instruments will cover the whole planet, as well as exploring its gravity field.
One of the special things about Mercury is that it's the only planet besides Earth who has a magnetic dipole field. And so we would like to understand the dipole around Mercury, or how the magnetic field around Mercury is interacting with the Sun. And that's very important for us, because then we can learn for Earth how the Earth's magnetic field is interacting with the Sun. And we have a lot of satellites around Earth which are affected by the solar wind and the interaction. So if we can get some clues about processes on Mercury, we want to learn for Earth.
Bepi Colombo's launch has been set back by minor hardware issues. Now scheduled for late 2018 launch, it is expected to reach Mercury in 2025. With the go-ahead from NASA, the Europa Clipper mission is underway, with the selection of instruments to fly on the spacecraft hopefully in the early 2020s. Its mission is focused on the Jovian moon Europa, believed to hold an enormous ocean of water beneath its icy surface. Europa's proximity to Jupiter and its speedy orbit cause the moon to stretch and contract under gravitational forces, generating mechanical heat within the core and providing enough energy to maintain a liquid ocean. Close inspection of surface areas also predicts that ice movement on the surface, similar to glacial movements, could allow for the formation of liquid water lakes close to the surface. One more place to search for those elusive signs of life. Is the cost of space exploration really worthwhile? It's a question that crops up regularly. Could the money be better spent elsewhere? Even if it were, one space program would still have to remain in place. That's the Planetary Defense Program, to locate, identify and deflect any wayward asteroid from hitting Earth and destroying our civilization. At the last count, there were 15,000 potentially dangerous candidates close to Earth. It's now over 2 years since the Rosetta mission reached its target rendezvous, 67P. It's been an audacious mission, gaining unprecedented forensic knowledge of the comet's surface, interior structure, composition and history.
We've noticed that there is not ice on the surface. We would be able to see that, at least not large patches of ice. You don't have skating rinks on this comet. And we also see gas in the coma. We see evidence of carbon monoxide and carbon dioxide and the elements themselves of carbon and oxygen in different parts of the coma.
And we discovered that this carbon was actually a very complex material, very complex carbon, very different from the simple molecules that we would expect to find there. So we don't see amino acids or alcohol or this kind of molecules which is observed in the gas, but we see something much more complex and very rich in carbon and poor in nitrogen or hydrogen compared to these other materials.
In particular, what we have observed is that the nucleus is composed of a mixture of materials like minerals, like silicates and sulfides, which have been formed in the inner part of the solar system, close to the sun.
Because the comet is kept in a very cold environment, we don't expect it to have very high temperature phases, so it can be that this material was formed closer to the sun and was then brought to the comet later. And this for us was a surprise because we knew it for the minerals but not so much for the organics. So it seems that the organics also can be transported over large distances in the solar system.
The most prominent, the most exciting changes on the surface, I believe it is still the big drop in the Imhotep plateau, which was 3 meters and 100 meters in height and hundreds meters in radius. But we have seen smaller scale features like a boulder, which was at least 50 meters big. It was 10 tons heavy, which, well, on the comet is just a chocolate bar of 100 grams or so, but still it's a massive thing, which has moved by 140 meters. Likely due to activity, but we don't know the real reason.
It was time to decide what to do with Rosetta now its mission was complete. One option was to land it on the comet.
There were discussions about what would be the priority for the end of missions. So there were several scenarios put together, and one of the options was to do those very close flyovers. And I mean, in terms of the science objectives, that was the one that will bring us the more interesting scientific results. So it was decided by the science working team to go for this scenario. So yes, that's a very first, again, another first of Rosetta.
Rosetta's trajectory was altered to spiral into the comet, taking photos as it closed in.
Rosetta's blown it all open. It's made us have to change our ideas of what comets are, where they came from, and the implications of how the solar system formed and how we got to where we are today. And we've only, like Philae, just scratched the surface. And it's important to note, Rosetta mission is both the lander and the orbiter. Together, they have made it possible to do the science, to make the breakthroughs that we have. And we have only just scratched the surface. We have decades of work to do on this data, so the spacecraft may end, but the science will continue. That's what we're here for. That's what this mission was for.
We just have had a loss of signal at the expected time. This is another outstanding performance from Flight Dynamics. So we'll be listening for the signal from Rosetta for another 24 hours, but we don't expect any. And so this is the end of the Rosetta mission. Thank you and goodbye.
One major problem faced by Rosetta and its Philae lander was low gravity. When the lander's harpoons failed to secure it to the comet, it tumbled and bounced until it was lost in the rugged terrain. But engineers love a challenge, and they have already come up with a novel answer for next time. It's called the Hedgehog.
So instead, together, JPL and Stanford have been working on a totally different rover concept that is well suited to these environments, called Hedgehog. Instead of rolling around on wheels, the Hedgehog design actually puts 3 flywheels on the inside of a cube. By spinning these flywheels up very slowly and then very quickly applying a brake, which transfers all the momentum from the flywheels, we're able to cause Hedgehog to either hop or tumble or perform small adjustments. So we've done many tests here on Earth in gravity offloading test beds. Recently, we have flown 2 Hedgehog prototypes on a zero-G aircraft. In these tests, we demonstrated that we would be able to perform on a comet or an asteroid. Hedgehog doesn't have a right way up. Instead, it can tumble over the surface and come to rest on any one of its faces and still work perfectly.
JAXA's sample mission from asteroid Itokawa from the last decade returned mixed results. It did, however, teach engineers and designers many lessons about the difficulties of collecting samples from asteroids. Their second attempt is currently underway. Hayabusa 2 is coasting towards another asteroid, Ryugu, and should reach its destination in the middle of next year. This new and improved robot has several new capabilities built in. They include ion engines, navigation and attitude control systems, and an explosive device to dig into the asteroid and return material from within it. Also on board are a probe and 3 miniature rovers. A secondary probe launched with Hayabusa, called Procyon, had an engine malfunction and will not complete its mission. NASA's attempt at an asteroid sample return is also underway. OSIRIS-REx was launched from Cape Canaveral Air Force Station's Space Launch Complex 41 and is on its way to intercept the near-Earth object Bennu.
2, 1, and liftoff
of OSIRIS-REx, its 7-year mission to boldly go to the asteroid Bennu and back.
Bennu is a B-type asteroid of approximately 500 meters diameter. It completes an orbit around the Sun every 1.2 years, and every 6 years it comes very close to Earth. These close encounters mean there is a high probability of Bennu's impacting Earth in the late 22nd century. Bennu's size, primitive composition, and potentially hazardous orbit make it the ideal OSIRIS-REx target asteroid. It will first survey the asteroid to find an ideal touchdown site.
Understanding the shape of asteroid Bennu is going to be absolutely fundamental to understanding the geology and putting it in context. The other reason you really need to understand the topography extremely well is that when we're going in to take a sample, it's a very, very fine measurement. And so if you're coming in, you've got the sampling head at the end of this arm that has to come in perfectly square to the surface. If you don't understand shape, sort of at a 30 centimeter scale, you're not going to be able to collect a sample.
The 7-year mission will see OSIRIS-REx touch down for only a moment to retrieve a surface sample of the asteroid, then return to Earth to deposit the sample return capsule somewhere in Utah in 2023. NEOWISE has been a reliable workhorse, operating long past its planned lifetime, but its mission will eventually come to an end. Engineers estimate it will move into too much sunlight to function. However, the team is eyeing a new space telescope, one with a little more muscle. The Near-Earth Object Camera, NEOCAM, is specifically designed to hunt asteroids. The proposal has been funded for further study by NASA. Undergoing preliminary work is the Asteroid Impact Mission, AIM, whose launch could come as soon as 2020. A joint NASA-ESA project would see ESA launch AIM to a binary asteroid, Didymos, and its satellite, Didymoon. They were discovered over 20 years ago and are part of a group of asteroids called the Apollo Group, near-Earth objects that cross Earth's orbit and are a potential threat. ESA's part of the mission is to orbit and study the asteroids, in particular their orbits around each other.
AIM will rendezvous with asteroid Didymos in June 2022. The first thing it will do is to take high-resolution images so that we can reconstruct a 3D shape of the moon. And then we will use this data to test a new optical communication system with a laser transmitting these images down to Earth in a very quick way. After we do these measurements and we have the 3D model, we will sound the interior structure of the asteroid by deploying a small microlander on its surface that will emit the small radio waves that will be captured by AIM and reconstruct the interior structure. After we have done these measurements, the spacecraft will move away about 100 kilometers from the system, waiting for DART to arrive and impact the Moon.
NASA's contribution DART is a kinetic impactor traveling at 6 kilometers per second.
Once the impact has occurred, then we will look at the ejecta and the dynamics of the ejecta cloud. We'll come closer to the Moon and repeat the same sets of measurements so that we can understand the changes in the interior structure and the shape and the morphology of the crater before and after the impact. AIM is the first mission to test the kinetic impact deflection technique. It's the first mission that will prove deep space optical communication systems, and it's the first mission to deploy CubeSats in this space and test inter-satellite communication systems. Also will be the first mission to rendezvous with a binary asteroid and characterize it so that we can understand how these bodies are formed, which is highly linked to the way the solar system has formed.
By measuring Didymoon's physical properties and its orbit before and after DART's impact, scientists will gain valuable knowledge that can be applied to a real threat should it ever occur. NASA is proceeding with long-term goals such as a manned sample return from an asteroid. A robotic spacecraft would locate and capture a small asteroid and redirect it into a lunar orbit. An Orion capsule would then rendezvous with it. Astronauts are now training and developing techniques for such a complex mission. There are still many things to be learned about asteroids and the dangers they might pose. As this animation shows, the inner solar system is awash with asteroids. Many of them are near Earth's orbit. Some even cross our path from time to time. All these possible hazards need to be identified, their orbits must be calculated to a high degree, and their threat assessed. Finally, we need to develop the technology to mitigate any danger to our planet. There are several groups of asteroids based on where they orbit. Those within Earth's orbit are Atens and Amors, while the Apollos cross Earth orbit. The majority of asteroids reside in the main asteroid belt between Mars and Jupiter. Then there are the Trojans, trapped within Jupiter's gravitational pull. And beyond that, other remnants of the solar system's formation can be found caught in the orbit of Uranus. There is a great deal more to be learned and understood about these other asteroids. To this end, 2 new asteroid missions have been planned and funded through the development stage. They will study 2 very different types of asteroid. The first of those missions is Lucy, which will visit a target-rich environment of Jupiter's mysterious Trojan asteroids. The mission will launch in October 2021 and fly by its targets between 2025 and 2033. In all, Lucy will study 6 Trojans and 1 main belt asteroid. Trojans are fossils of planet formation, and so will supply important clues to the earliest history of the solar system. The second is Psyche. This mission will explore one of the most intriguing targets in the main asteroid belt, a giant metal asteroid known as 16 Psyche. About 3 times farther away from the Sun than the Earth is, this asteroid measures about 210 kilometers in diameter, and unlike most other asteroids, which are rocky or icy bodies, is thought to comprise mostly metallic iron and nickel, similar to Earth's core. Psyche could possibly be the exposed core of an early planet, which lost its rocky outer layers in violent collisions billions of years ago. The mission will help scientists understand how planets and other bodies separated into their various layers: cores, mantles, and crusts. Psyche will map features, structure, composition, and magnetic field, and examine a landscape unlike anything explored before. For an instrument first developed as recently as the 17th century, the telescope has traveled a long way. The latest version of the once humble telescope will be going a lot farther, carrying us ever closer to the first light that ever bathed the universe in which we live. Generational change is part and parcel of our lives. In terms of space exploration, the Hubble Space Telescope has been doing its extraordinary work for a generation now, and it's time to hand over the reins.
What we've reached is the limit of Hubble's vision. As amazing as Hubble has been, we've come up against the immutable reality that Hubble can't, in fact, see everything.
Galileo, Herschel, Hubble. Our knowledge of space is marked by some of the greatest names in the human history of stargazing. But who was James Webb? His name is attached to the James Webb Space Telescope, which will soon be helping us understand what lies beyond even the amazing reach of Hubble. Originally called the Next Generation Space Telescope, Hubble's successor was renamed in 2002 to honor James E. Webb, who ran NASA from February 1961 to October 1968. Those dates, of course, put Webb at the heart of the American space program, and the moon landing in particular. But that was not Webb's sole preoccupation. Webb's energy encompassed robotic spacecraft, probes to Mars and Venus, and in 1965, his advocacy of a large space telescope. He was, in other words, a man of vision. The James Webb Space Telescope is nearing completion, in readiness for a scheduled launch in October 2018. By a happy coincidence, exactly 50 years since James Webb's tenure at NASA ended. Its aim is modest, to study every phase in the history of the universe. Several major agencies have collaborated in the creation of the James Webb Space Telescope. NASA's Goddard Space Flight Center is at the hub. ESA will provide the launch vehicle, the ultra-reliable Ariane 5 rocket. Canada's space agency is involved, as is the Space Telescope Science Institute, while Northrop Grumman is the chief contractor.
The Webb will be wonderful for the astronomy community. Not only will it give them the kinds of wonderful resolution we have with Hubble that you can get above the atmosphere, but it's going to bring them access to a wavelength region where many of them have not worked before.
We have a telescope that's far more powerful than anything that we have had before, working at infrared wavelengths, which you can't see well from the ground. And that will enable us to see things from the most distant universe that we can only guess at, things in the outer solar system that we can only guess at.
The Webb is going to be such a powerful telescope. It's going to be like the Hubble. And in the case of the Hubble, probably more than half of the greatest observations, discoveries that the Hubble made were things people didn't anticipate. I expect the same for the Webb.
The James Webb Space Telescope's mission duration is a planned 10 years, during which it has a number of specific goals to accomplish. It will search for the first galaxies, determine how galaxies were formed, observe the formation of stars, and measure the properties of planetary systems, both physical and chemical, including our own solar system. Not least of all, the Webb will carry on the task that underlies so much of humankind's activity in space, investigating the potential for life in other far-flung places. The 6,200 kilogram space-based element of the Webb will not orbit Earth, as Hubble has been doing. Instead, it will orbit the Sun. To do so, it must first travel 1.5 million kilometers, a 30-day journey to L2, the Lagrangian point at which the gravitational forces of Sun and Earth are roughly equivalent. Each orbit will take 6 months and keep the JWST out of the shadow of both Earth and Sun. Its trajectory also makes 24/7 communications possible. The Webb will stay in line with Earth as it moves around the Sun. And that is because, while the James Webb Space Telescope is looking for first light, its first task is to find darkness, the condition in which it can operate at its best. Three main component systems make up the space-based James Webb Space Telescope: an integrated science instrument model, ISM, the optical telescope element, OTE, and the spacecraft element. The key to the JWST's enhanced vision is its primary mirror, which measures 6.5 meters across. It comprises 18 segments made of beryllium, the lightest of the alkaline earth metals. A 5-layer sun shield the size of a tennis court will protect the JWST's dazzling array of specialist technology. As this orbiting infrared observatory continues the work begun by Hubble. On board are a near-infrared camera, a near-infrared spectrograph, a mid-infrared instrument, a near-infrared imager, and a slitless spectrograph. The NIRSpec has micro-shutters, which will make it possible to observe up to 100 objects simultaneously. The Webb's cameras and spectrometers are capable of detecting extremely faint signals, a crucial factor in its attempt to see as far back as first light. While NASA busies itself with James Webb, its European counterpart ESA is hard at work on another related mission with a much more famous name attached to it. Euclid is named for the Alexandrian Greek whose geometrical study, the elements, formed the basis of our mathematical thinking for almost 2 millennia.
What we want is actually to continue our successful program, which is actually providing the cutting-edge space science, meeting the challenges of worldwide research.
But where the original Euclid worked only with ruler and compass, his namesake in space will have much more sophisticated instruments in its locker. Like the Webb, Euclid boasts a modest mission to map the geometry of the dark universe. Over a period of some 6 years, it will look back over the entire time in which dark energy has contributed to the accelerating expansion of the universe. Scientists tell us that what we can see accounts for less than 5% of what is there. The rest is made up of dark matter, some 20%, and the remainder of dark energy. They act in contradictory ways. Dark matter acts through gravity to play its role in forming galaxies and slowing the rate of expansion of the universe. Dark energy, on the other hand, defeats gravity and thus encourages acceleration of that expansion. The Euclid Consortium, part of ESA's Cosmic Vision program, brings together 1,000 scientists from 100 institutes in 14 countries with added input from NASA in the United States. In 2013, Italy's Thales Alenia Space Group was named as prime contractor, with Airbus in France responsible for the payload module. On board Euclid's payload module will be a telescope 1.2 meters in diameter, a visible light camera, and a near-infrared camera and spectrometer. Euclid will undergo its critical design review in 2017, with its launch planned for December 2020 from Kourou in French Guiana. Like the JWST, it will orbit around the L2 point. Channeling the thinker whose name it bears, Euclid will be looking for genuine insight into the evolution of cosmic structures. Investigating the nature of dark energy, dark matter, and gravity, it will track their observational signatures on the geometry of the universe and on the cosmic history of structure formation. Euclid will deploy 2 key systems: weak gravitational lensing, or WL, and baryonic acoustic oscillations, BAO. WL examines how background galaxies are disturbed by foreground dark matter and measures modifications in the shape of galaxies brought on by the gravitational lensing of dark matter. BAO reveals the wiggle patterns which help us gauge the expansion of the universe, revealing the three-dimensional distribution of structures by means of the spectroscopic red shifts of galaxies and galaxy clusters. Putting it more simply, perhaps, Euclid's task, made easier by its unprecedented accuracy and stability, is to map the shape, position, and movements of 2 billion galaxies, or 1/3 of the sky. Even more excitingly, the James Webb Space Telescope is not the only star performer, pardon the pun, on the horizon. In 2016, NASA confirmed the decision to go ahead with its Wide Field Infrared Survey Telescope, or WFIRST for short.
WFIRST is a NASA observatory that has the top ranking of the National Academy of Sciences to launch in the 2020s. It has the same image precision and power as the Hubble Space Telescope, but with 100 times the area of sky that it views.
Looking at a large fraction of the sky allows you to get a more complete accounting. For example, the stars in the Large Magellanic Cloud, which is the nearest galaxy to us, or the stars in the galactic bulge. So you can do a much more complete accounting in a much shorter amount of time.
This new observatory will offer astrophysicists the best of both worlds by casting its eye both wide and deep as it seeks to shed light on dark energy, exoplanets, and cosmic acceleration. Surveying large areas in near-infrared light, a single image from WFIRST will have all the depth and sharpness to which Hubble has accustomed us, but will cover 100 times the area. In fact, a single image will encompass as many as 1 million galaxies. The new telescope's work will slip into the groove already made by Kepler, the Sloan Digital Survey, and TESS, the Transit Exoplanet Survey satellite. WFIRST will use microlensing rather than the transit method of detection. It will employ a 2.4-meter diameter telescope provided by the National Reconnaissance Office. But the best of both worlds part of the WFIRST story comes with the coronagraph, which NASA has been able to add to its instrumental array. This is a means of dimming the light from a so-called host star in order to see better the planet or planets orbiting it. And that is highly significant if we remember that the host star may be up to 1 billion times brighter than any exoplanet identified. If successful, the coronagraph technique will make it much easier to determine the chemical composition of planetary atmospheres. WFIRST will be able to use a unique deformable telescope controlled by computer. This first mission, due for launch in the mid-2020s, being what is called a technology demonstration, laying down a scientific marker for future missions to go in even more determined pursuit of life beyond the confines of our own solar system. While all of this is going on in space, Here on Earth, another agency will be tackling the question of dark matter from yet another angle. At CERN in Geneva, the Large Hadron Collider is now running at full power for the first time.
The very exciting and intriguing possibility that in addition to gravity, there might be a new force between our visible matter and dark matter, which is transmitted by a new photon-like particles, which we call dark photon or heavy photon or paraphotons. There are many different names for these particles. This experiment, it's apparatus which is about 30 meters long, and the main idea is that we search for so-called invisible decay of dark photons. And these particles could be quite light, below 1 GeV, and what is most important that these particles could be searched for at low energy experiment, with fixed target experiment.
So what you see here is the beam pipe where the beam is coming. The electrons are deflected by two magnets, which are about 15 meters upstream. The purpose of that is really we need to be sure that what we get here are electrons of 100 GeV. So in this magnet, when the electrons are deflected, you generate synchrotron radiation, and this we detect with this detector here.
So the idea is that when the high-energy electron collide with the active target, which is electromagnetic calorimeter, it's create in this high-energy collision with the nuclei, create dark photons, which carry away from the setup significant fraction of the primary energy. So the experimental signature of the existence of A prime is an event with such missing energy, and we search for these events with this setup.
Stars are a bit like human beings. They can be warm or cold, they come in all kinds of shapes and sizes, and, let's face it, they can be dim or bright. And recent discoveries suggest that the number of stars in our galaxy alone, the Milky Way, may exceed 200 billion. Just what are these citizens of the night sky? Days are numbers, count the stars. It's the first line from a popular song, but the one after is more relevant. We can only see so far, it says, and it sums up perfectly our relationship with the stars that matter so much in our lives. What is a star in the first place? Well, a star is to the cosmos what a key player is to a team, a ball of energy just waiting to be unleashed. Stars are essentially bodies of hot gas arising within a nebula, which itself is simply a cloud of dust and gas within a galaxy. Most famous perhaps is the Eagle Nebula, with its stunning pillars of creation. Each nebula is like a cosmic kindergarten, from which bright young things are just bursting to escape. We call them stars. Suggestions are that 7 new stars form each year within our Milky Way alone. What trips the wire to kick-start the formation of a star? Usually it will be one of 3 events. The effect of an explosion from a nearby supernova, the nebula's moving through a particularly crowded pocket of space, or a flirtation with another passing star. At some stage, an area of high density within a nebula will resolve itself into a globule of gas and dust, which will then contract under the force of its own gravity. This condensing matter heats up. As the density increases, this protostar, that is to say the first iteration of the new heavenly body, starts spinning around a central axis. A new star exists in what scientists call hydrostatic equilibrium. The inward force of gravity is balanced by the outward pressure from the star's core. If there is sufficient matter, a nuclear reaction will take place, releasing a huge burst of energy, which must find its way from the new body's core to its surface. This process takes place over an enormous time span through a combination of radiation and convection. Next time you go to the beach, imagine trying to count every grain of sand, not just the ones you see, but all the others below. Then turn that idea on its head and imagine trying to count the stars, all those we see and those we don't. ESA's Gaia telescope is making that seemingly impossible task more like a reality. Its full map of the night sky is due for completion this year, but already preliminary data covering 2 million stars has been released, and the scientific world is very excited.
We want to measure a huge number of stars, where they are and how they are moving. So we can answer two questions at the same time. What is the structure of our galaxy, but also how it is evolving, or we can also look back in time. How did the stars move to come into the place where they are now?
The mission's technical measurement principle is there are two fields of view, two cameras basically looking at the sky at a very constant and fixed angle, and it rotates along the sky, so it traces a path along the stars. It then uses these measurements to determine the position of stars relative to each other, and then you can get to extreme accuracies also for the absolute position of these objects. The data comes down to the ESA antennas on the S-track network in Argentina, in Spain and in Australia. From there it goes to Darmstadt, who control the spacecraft, and then it goes to our central data processing hub near Madrid in Spain, which is an ESA center. And from there it goes to the data processing consortium, which then slices it up in different parts and processes this into science products.
Our first release will contain positions of 1 billion stars. So that will allow us to look, what does the night sky really look like when you would look at in random direction with a telescope which can see very faint stars. And a subset of 2 million stars, we will have the distance and the motion. So that is really the basis for astronomical studies. People can really look into details of these sources and study the behavior of the stars. And in addition, we have light curves for about 3,000 stars, so how they have been varying over time to analyze better the internal structure of these stars.
Eventually, it will plot the position and movement of 1 billion stars in our galaxy, the Milky Way. Astrometrists still have their work cut out, but thanks to Gaia, the job of counting the stars just got a whole lot easier. Something remarkable happened in November 2016. Astronomers discovered a new way of witnessing a star's formation. Adding to the familiar methods of transit, gravitational lensing, and direct imaging, they found a new little friend, quite literally. Chandra, the world's most powerful X-ray telescope, is part of the great observatory that includes Kepler and Spitzer. It orbits Earth some 140,000 kilometers out and is capable of fine definition of hot, turbulent areas in space. Little Friend acted as a mirror, deflecting X-rays from Cygnus X3 towards Earth to help astronomers identify stars coming into being. In conjunction with the Smithsonian's Submillimeter Array SMA system, it detected carbon monoxide and the outflow of gases, which suggest a new star in formation. This is the first time scientists have been able to use X-rays to peer into a Bok globule, one of the focal points of star formation. The nomenclature of stars derives from their size, which is in part a function of the phase of their life they are going through. A life, incidentally, which may extend to trillions of years. The range goes from red hypergiant at one end of the scale to white dwarf at the other, smaller end. Those at the large end are far larger than our Sun. They may be billions of times greater in volume. Dwarf stars abound. The Sun is a yellow dwarf, for example, with a surface temperature of 5,500 Celsius, while red dwarfs like Proxima Centauri are stars on their way to becoming white dwarfs. What remains of giant stars whose light, put simply, is failing. The process of a star's birth culminates in the fusion of the hydrogen at its core into helium, a process called the main sequence, to which the majority of stars belong. Red dwarfs are not only the most common, they are the most durable. They burn at the low end of the surface temperature range at around 3,500 Celsius. In massive stars, the hydrogen to helium conversion is much faster. Paradoxically, the bigger the star, the shorter its life. How else are stars classified? Basically by two criteria: brightness and color. Stars are catalogued by their magnitude, either apparent or absolute. Apparent magnitude, as its name suggests, refers to the luminosity of stars as seen from Earth. This may vary, of course, according to the mass of the star itself, and especially its distance from us. Absolute magnitude corrects that by establishing the star's luminosity as detected from a standard distance. Paradoxically again, the brightest carry the lowest orders of magnitude. A century ago, working independently on opposite sides of the Atlantic, Hertzsprung and Russell came up with the same basic methodology for classifying stars within a spectroscopic range according to the light generated by their wavelengths. The scale runs from O to M, and, to cite some examples, from the blue of Zeta Puppis to the red of Betelgeuse or Betelgeuse. Made any holiday plans recently? If you're a stargazer, then NASA's own travel bureau may have just the thing for you. While a trip to another world may not be within your budget just yet, astronomers are making us increasingly aware of the heavenly bodies above us and planning on getting us there. When set alongside exotic places like Monaco or Morocco or wherever, the holiday destinations advertised in NASA's graphic travel bureau may not seem too enticing. But they are certainly, to use a travel agency cliché, out of this world. The striking images, genuine postcards from the edge we might call them, include HD 40307G. That's the very down-to-earth name for an exoplanet which astronomers call a super-Earth. One of those revealed by the Kepler Space Telescope on its so-called K2 mission when it bounced back from a mechanical failure in 2014. Could there be at least one planet orbiting every star in the galaxy? Already more than 3,000 of them have been confirmed, with almost the same number awaiting confirmation. The nearest to us is Proxima Centauri b, a mere 4 light-years away from Earth, in the triple star system of Alpha Centauri. Proxima Centauri b, excitingly, is an Earth-sized planet in the star's habitable zone, the distance at which liquid water may form on its surface.
Astronomers have found clear evidence of a planet orbiting the star Proxima Centauri. This alien world is the closest possible abode for life outside the solar system.
The idea of celestial harps is not new, but in real down-to-earth life there is indeed a harps at the center of the search for life elsewhere in our skies. It's ESO's high-accuracy radial velocity planet searcher, or HARPS for short, which is a spectrographic instrument attached to the 3.6-meter telescope at La Silla in Chile. Reflecting our connected age, in 2016, ESO invited members of the public to follow live as it embarked on a determined search for proof that circling Proxima Centauri there was, as suspected, an exoplanet, the pale red dot that gave its name to the program. Not just any exoplanet, Proxima b, as it had been labeled, is the likeliest one so far discovered with a chance of playing host to life. In late summer 2016 came the thrilling news. Close examination of the gravitational pull of the exoplanet and its wobble effect on its host produced what ESO calls clear evidence for a potentially habitable world, 1.3 times the size of Earth, and in an 11.2-day orbit around its star. Ultraviolet and X-ray radiation levels on its surface appear high, and the exoplanet is much nearer to its host than we are to our Sun. But ESO next plans to use its forthcoming extremely large telescope, the ELT, and later interstellar probes to get even closer to solving the enigma of Proxima b. Where do stars go when they die? That depends on their size, or rather on their mass. Stars of high mass will follow one of two paths. Nearing the end of their life, as the core of the star collapses, it will give rise to a supernova. The gigantic explosion triggered when the output of energy at its core suddenly ceases. Scientists are predicting that Betelgeuse, the red giant in Orion, whose mass may be as much as 20 times that of our Sun, is on its way to a supernova within the next 1,000,000 years. The end product of a supernova will be either a new, different kind of star, or that great unknown, a black hole. On one hand, the core may survive as a neutron star, which may measure the remarkably small diameter of 10 to 20 kilometers. Not only that, but they are of extraordinary density. A teaspoon of their substance would weigh in the millions of tons here on Earth. Neutron stars often act as the lighthouses of the sky as well. Because of their strong magnetic field and fast rotation, they emit polar radiation beams, discernible when the beam is directed towards Earth, just as the beam from a lighthouse will be visible out at sea only in fleeting cyclical movements. The other possible fate for a dying star is to become a black hole. While there is a plurality of objects in our sky, black holes bring us face to face with a singularity, the point at which matter is compressed. The singularity will be either a point of infinite density or adopt the shape of a ring. Either way, its gravitational pull is so strong that nothing, not even light, can resist or escape it. Its boundary is described as the event horizon.
90% of black holes in the universe don't have a lot of hot material orbiting around them. They don't form these accretion disks, and so we can't observe them. Tidal disruption events, where the stellar debris causes the formation of a temporary accretion disk, offers us a way to probe this population of supermassive black holes.
One tool astrophysicists use to stare into the abyss is X-ray reverberation mapping.
X-ray reverberation mapping has been very successful at probing the accretion flow in well-established accretion disk structures, but had never been used to look at tidal disruption events. My collaborator at the University of Maryland and I were having lunch one day, and she says, "Has anyone ever looked at tidal disruption events with X-ray reverberation mapping?" That night, I stayed late at the office and just tried it out on this data from Swift J1644, and much to my surprise, the result was amazing, and I could see that we were looking at the structure of the inner accretion flow around a normally dormant black hole for the first time. It's not like a normal accretion flow in an active galaxy that's a flat disk. This is something that is extremely puffy, very turbulent, and we are measuring flashes of X-ray emission deep within this newly formed accretion disk. Previously, astronomers had thought that the X-ray emission is coming from far out in a jet. But what we're finding with these observations is that the X-ray emission is coming from flares very close to the supermassive black hole. And we can use these observations to probe properties of the black hole itself. For instance, we found that the mass of the black hole is something on the order of 1,000,000 times the mass of the Sun.
The Milky Way, which contains our solar system, is itself part of a so-called local group of galaxies, including, for example, Andromeda, which in turn belong to the Virgo supercluster, 100 million light years across. When we've had a bump on the head, we say we're seeing stars. Looking at it from an astronomical point of view, the number of stars out there is enough to make anyone's head spin. Perhaps that American politician was right. There are indeed things we know we don't know. For instance, cosmologically speaking, we know we don't know much, and certainly not nearly enough, about two of the enduring mysteries of the universe, dark matter and dark energy. It's little wonder that scientists are devoting so much grey matter and energy of their own to finding out as much as they can. Seen any big birds recently? Ice Cube has. If you think that's a cool name, you're right. Ice Cube is an observatory at the South Pole, and it saw Big Bird back in December 2012.
Ice Cube is a neutrino telescope located at the South Pole, or to be more precise, under it. It consists of over 5,000 detectors that are spread out into a cube about 1 kilometer on each side. It's the world's biggest and its coolest telescope. Ice Cube has detected a handful of extremely energetic neutrinos. One of them, which is called Big Bird, has an energy of about 2 peta-electron volts. To give you an idea of how much energy that is, it is about 1 million times the energy of a dental X-ray.
Scientists have been using the names of critters from the popular TV series Sesame Street to designate major events that may help us better understand the particles that emanate from space. Particles like neutrinos.
So a neutrino is an incredibly small particle. It moves almost at the speed of light. It is nearly massless. It's incredibly plentiful, but it's very, very hard to detect because it will not interact with just about anything. If you could detect them though, because they have traveled through the universe essentially undeflected, they have information that you could not access in any other way.
The theory is that neutrinos are caused by violent events in space. In 2012, light from such an event began reaching Earth. This was a year-long outburst which happened 10 billion years ago in the unromantically named galaxy PKS B1424-418.
What we have been able to establish for the first time is an individual blazar as a potential birthplace of an individual neutrino. The Fermi Gamma Ray Space Telescope has an instrument called the Large Area Telescope, which we use to monitor the gamma ray sky, the highest energy electromagnetic band. And we just noticed that there was a tremendous increase in the amount of gamma ray light coming from this one extragalactic blazar. A blazar is an extremely powerful, variable galaxy that is powered by a supermassive black hole. It went up not by a little bit, not by a few percent. It went up like 15 to 30 times its average flux. So we knew something was afoot. Later on, it turned out to be coincident both in time and in space with the neutrino that was detected by Ice Cube.
Working in conjunction with NASA's Fermi X-ray telescope, Ice Cube was able to link the cosmic neutrino it observed with that outburst from the gamma ray blazar. The first time such a causal link between neutrinos and a single extragalactic object had been established.
The enormous increase in gamma ray flux seen by LAT and radio flux by other Tanami telescopes let us finger the exact blazar which is responsible for Big Bird. This is the first time that we can point and say that blazar is where this neutrino came from.
Neutrinos and gamma rays are what Fermi is all about. It has already made some startling discoveries. One of its latest is finding the most distant and oldest blazars. Blazars are a type of galaxy whose intense gamma-ray emissions are powered by supersized black holes. These distant objects emitted their light when the universe was 1.4 billion years old, or just 10% of its present age. That they developed so early in cosmic history challenges current ideas of how supermassive black holes form and grow. Fermi has received an upgrade to improve its capabilities.
We see gamma rays, which are the highest energy form of light. And with each object that we see these gamma rays from, what we're doing is exploring some of the places in the universe with the most extreme environments.
The kinds of objects that we can study are pulsars and neutron stars, black holes, as well as dark matter.
So, to analyze these events, we have written a very long and complex program that basically uses all the information that was recorded by the instrument and figure out what is the direction of the gamma ray, its energy, and whether or not it's a real gamma ray and not a charged cosmic ray. So obviously software is really important for the LAT.
The software that we use to analyze the LAT data has gone through many revisions over the course of the mission. But PAS-8 is really the first revision of the software where we took into account all of the experience that we gained from operating the LAT in its orbital environment.
PAS-8 has made everything better, but one of the things that it's made better is that it's allowed us to open our gamma ray eyes to higher energies before, so that's a completely new view, and it's allowed us to open our gamma ray eyes at energies lower than before, so that's another completely new view, in addition to improving everything across the entire energy range.
The improvements that we've made to the software retroactively apply to all the data that we've collected. And so these improvements significantly enhance what we can do with the data that we already have, as well as the data that we'll collect.
Fermi's talents have also been concentrated on the search for dark matter, and in doing so it has observed unusual behavior in objects that remain unexplained. For instance, Fermi has discovered a gigantic structure in our galaxy, with what looks like bubbles extending above and below the galactic center. These are enormous gamma-ray emitting lobes. Each lobe is 25 light years tall, and the entire structure may be only a few million years old. Within these clouds, extremely energetic electrons are interacting with low-energy light to produce gamma rays, but no one knows the source of these electrons. When studying these massive objects, scientists must look at the other end of the size spectrum for answers. Those at CERN in Switzerland are expecting great things from the Large Hadron Collider, after it too received an upgrade, an increase of power by 40%. In its new improved form, it is due to produce far more data than it previously did. The LHC has already revealed the Higgs boson particle. One of two types of fundamental particle, fermions or the other, in our standard model of the universe. What other secrets might it be about to unearth, as it were?
With an increased luminosity, we gain sensitivity at the highest energy. So suddenly, we will explore energies that hitherto were not really reachable. So if new physics is hidden there, this is the chance to see it. Some indications that created a lot of excitement with the theorists were seen with the experiment as there may be fluctuations, there may be real particles. As a physicist, of course, I hope that this is new physics already. But maybe that would be too simple.
The Higgs boson was the last puzzle piece in the standard model of fundamental particles and the forces which govern them throughout the universe.
What we really want is to understand the universe and why it looks and acts the way it does today. Our role as particle physicists are to figure out what the elementary particles are and how they fit together and interact, kind of like puzzle pieces, and the way the puzzle pieces fit together to give us a picture of the universe. Over the last 120 years or so, we've discovered all the individual puzzle pieces that build up to give us a theory called the Standard Model, which is kind of like the picture on the box. But we know that it's an incomplete theory. What we've essentially got is a small section of a puzzle picture that fits together very nicely and gives us all the particles that we see today, but we have no idea what the bigger picture is. The Higgs boson that we discovered in 2012 was the final piece in our Standard Model puzzle, and it was a fantastic discovery because it completed that small picture. And now what we can do is possibly use this Higgs boson to access the other parts of the puzzle. So our Higgs boson becomes like a Rosetta Stone to talk between the Standard Model particles and these new, what we call dark sector or hidden sector particles. So we're going to need to create many, many more Higgs bosons to be able to start seeing hints of this. And that's where the higher energy is useful. When we go to higher energy, it's almost as if we're getting a microscope to look on what we've discovered so far. It's possible that there are some very small differences in that Higgs boson, like the way that it decays, that we haven't noticed yet because we haven't had a strong enough microscope. But with a higher energy collider, with the LHC running at 13 TeV, maybe that is going to give us a strong enough microscope so we can see some small differences between our Standard Model theory and the Higgs boson that we have today. And maybe that'll give us some hint of some new physics that we can expect to come.
But it doesn't explain why nature prefers matter to antimatter, or what dark matter is. One theory that has been developed to answer these questions is what is called supersymmetry.
So one of the problems that supersymmetry could resolve is the mystery of dark matter. So this is something that astronomers and cosmologists tell us that there's an additional source of gravity in the universe which cannot be attributed to things we can see, the stars, the nebulae, and other things like that. And so at the moment this has the mysterious name dark matter. I think that's at least partly because we don't really know what it is. It's quite reasonable to think that it's a particle of a kind that we could potentially produce at the LHC, and supersymmetry, or at least some forms of supersymmetry, could explain that matter and predict its properties. So the main problem, if you ask most physicists, I think, that supersymmetry would explain is the mass of the Higgs boson. With the Standard Model as it stands, we cannot explain why the Higgs boson has the mass it has. It should be many times heavier than it actually is. So heavy that we would have no chance at all of seeing it in any foreseeable experiment. And this currently has no explanation. Supersymmetry would provide a very neat solution to that problem.
So, does dark matter? It certainly does. It makes up about a quarter of the universe. What is it? The short answer is, we don't know. The phrase was coined in the 1930s by Swiss scientist Fritz Zwicky. 4 decades later, Vera Rubin's studies of galaxy rotation confirmed his thinking. Galaxies have more mass than observable light would lead us to suspect. One suspect suggested by supersymmetry are the neutralinos, sometimes called WIMPs, or weakly interacting heavy particles. These particles act as their own antiparticle. They annihilate each other and release a flurry of secondary particles and medium energy gamma rays.
The LHC experiments are very capable to find dark matter. If, for example, supersymmetry is the symmetry which nature has realized, then I'm very confident that maybe even very quickly we can find, with the LHC experiments, supersymmetry. And that would be great. I mean, imagine we have taken roughly 40, 50 years in order to find and to really discover the Standard Model of particle physics. But that only explains 4 to 5% of the energy and matter density of the universe. I think LHC is the right machine to bring the first light, to shed the first light into the dark universe. There are more and more connections between space research and particle physics, but on the methodology, for example, and such things. But also on the science itself, there is a very strong connection, especially through dark matter. I mean, astronomers and astrophysicists will tell us in the next, I don't know, 10, 20 years with their new telescopes, they will tell us how dark matter, for example, has shaped the universe. And with the LHC, we will find what type of matter that really is.
These are some of the things we know that we don't know. But what if new physics tells us there are things we don't know that we don't know? The latest LHC data has turned up some interesting results.
In the data we took last year, we started to see a clustering of events, of diphoton events with 2 photons at a particular region of mass. The significance of that is not at this point very high. With more data, we don't know what's going to happen. There's a chance it could stay, but there's also a bigger chance that it will go away again. But which is going to happen, we don't know.
Physicists are keen to explore any glitch in the data.
The most exciting thing would be to find something that is completely outside the standard model. Even if it's just a hint that there is something more within our reach, just to give us an idea of where to look for new physics. There's got to be something out there. We know that our picture is incomplete, and we just have to find the right place to look for it.
For this year's running, we are running again at 13 TeV center of mass energy. But the big difference this year is we're going to run at a lot higher intensities, and we expect to get a much bigger data sample. So the experiment itself is ready and starting to take the data that's coming, and it really is shipshape waiting for the new data. At that point, of course, then we're looking in great detail and great depth at the data to try and understand what the physics is in the new data. And there's many different things we will be looking at with this new data sample. We will look again at the known processes of the standard model, which we've already seen at lower collision energies, and we started to understand and to measure with last year's data. But we'll also, of course, look hard at places where we might be able to see new physics starting to occur.
From the tiniest of subatomic particles to the immensity of galactic clusters, scientists and astronomers are looking into the past so as to see the future.
But when you think again about what we're exploring, when you think about the images that we're going to take, when you think about how far and away and how far back in time we're going to look, you can't help but feel like you're a part of something that's really important, that's helping us see not just about the past of the universe, but the past of us, where we've been and really where we're going to go.
If discovering the true nature of dark matter is successful, then we will have put together a picture of about 30% of the universe. There's still a lot more stuff missing, and it's called dark energy. Scientists have labeled dark energy one of the biggest mysteries in physics. Dark energy is the name attached to the force that appears to account for as much as 70% of the universe. Our fixation with dark energy dates from the late 20th century, when Hubble's brilliant revelation of supernovae showed us that the universe, approximately half its lifetime ago, was expanding more slowly than it is in our time. It started to speed up around 7.5 billion years ago. Why? Dark energy is the working name for the amorphous answer to that specific question. Is it a property of space itself? Does empty space contain its own energy? Does that energy increase as more space comes into existence? Dark energy has negative pressure. As dark matter is inimical to light, so dark energy repels gravity. At least that's how the theory goes. And to back it up, one major international effort is nearing the end of its scheduled working plan. Begun in 2013, the Dark Energy Survey, or DES, is an international project linking 400 scientists from 25 institutions in the United States, Australia, Brazil, Spain, the UK, Germany and Switzerland. Its chief instrument is a 570 megapixel digital camera, DCAM, attached to the Blanco telescope at Cerro Tololo in Chile.
I'm a member of the Dark Energy Survey Collaboration, and I'm here on Cerro Tololo working to help commission the new dark energy camera that we've just installed on the Blanco telescope. The whole purpose of our project is to understand what is dark energy. Dark energy was discovered just less than 15 years ago, actually. In fact, using, in part, this very telescope. And it was discovered by its effect on the universe. So dark energy is our name, and it's just a name that we give to the phenomenon that's causing the universe's expansion to accelerate.
We're not trying to figure out if dark energy exists. We're not trying to find it. We know dark energy exists. We're trying to characterize it. We're trying to understand what it does to us, what it does to the universe, to its expansion rate, and to the gravitational attraction of things like galaxies. Over 5 years, the Dark Energy Survey will scan 5,000 square degrees of sky, far back in time and far away from us, in order to measure the distances of supernovae and the distributions of galaxies.
In some sense, the purpose of our experiment and what we'll learn by understanding more about what dark energy is to find out about the fate of the universe. What is going to happen into the future? Is the universe really going to keep expanding faster and faster and faster, or not?
Covering 5,000 square degrees of southern sky, the DES project is due to complete its search in 2018. Like the DES, some other exciting discoveries lie potentially just around the corner. While space-based telescopes continue their tireless scouring of the skies, their ground-based counterparts are poised on the brink of a dramatic new age. More than 3,000 meters above sea level, at Cerro Armazones near Paranal in Chile, ESO's ELT, that's Extremely Large Telescope to you and me, is nearing the start of its working life. With its stunning 5-mirror system, its diameter is an unprecedented 39 meters, making it the largest optical and near-infrared telescope in the world. Extremely large telescopes are currently one of the highest priority areas of development in ground-based astronomy. On ESO's ELT's job list will be the continuing search for exoplanets, examining the possibility, for example, of establishing contact with Proxima Centauri b, one of the likeliest candidates for Earth-like biological conditions. The ELT, attracting 15 times more light than the largest telescopes in operation today, will help detect water and organic molecules, a major step forward in our quest for extraterrestrial life, and make possible direct measurement of the speed of acceleration of our universe's expansion. Will it provide some of the answers we seek? Or will it show us collectively that we don't yet even know what we don't know? Is gravity an illusion? Do we need a new theory of gravity on a cosmic scale? As Einstein himself observed, the most beautiful thing we can experience is the mysterious. The Soviet-era Luna 3 was the first spacecraft to use gravity to change course to photograph the dark side of the Moon. The NASA Mariner 10 mission used the technique to swing by Venus to target Mercury. The gravity assist or slingshot maneuver has become a standard for navigating the solar system, with our probes reaching further, faster and more accurately than ever before. The Voyager mission started by chance over 40 years ago, when Michael Minovich, a mathematics PhD student, decided to tackle celestial mechanics' holy grail. It was known as the three-body problem, as it looked at the Sun, a planet, and a third object traveling in space, and how gravity from the two objects affected the trajectory of the third. Minovich was eager to take advantage of IBM's latest computer, the 7090. This computer was a second-generation transistorized version of the IBM 709, a vacuum tube mainframe which had a processing speed of around 100 kiloflops per second, unthinkably slow by today's standards. The laws of physics and the conservation of momentum demand that the probe approaching the gravitational influence of the planet and accelerating will then decelerate upon leaving that gravitational field with a net speed increase of 0. However, the probe's speed and direction will change in reference to the Sun. His solution has become known as gravity assist or slingshot. While undertaking an internship at NASA's JPL, he convinced them to test his model using their data. The results confirmed his predictions that if it flew close enough to a planet, a spacecraft could utilize that planet's motion to accelerate itself away from the Sun. When Caltech graduate Gary Flandreau was tasked to see if gravity assist could aid deep space missions to the outer planets, he discovered there was to be an alliance of Jupiter, Saturn, Uranus and Neptune, an event that occurred only once every 176 years, an opportunity not to be missed. So it was decided to launch a mission in 1977. 2 spacecraft would be launched which would slingshot past all 4 of them, a grand tour of the solar system's outer planets in a 12-year time frame. This was to become known as the Voyager missions, and the rest is history.
Ultimately, we're able to put together a picture of where we are in the galaxy and how that environment then influences our environment right here at home. In particular, the radiation environment, which has implications for all sorts of things, including human exploration of space.
Today, those 2 spacecraft have continued on beyond the influence of our Sun into interstellar space, the farthest traveled by a man-made object. This field of influence formed the basis for all future missions, allowing man to set his sights on getting into deep space economically. The Rosetta mission had different challenges: to catch up with and orbit a comet, 67P Churyumov-Gerasimenko. It had a large elliptical orbit around the Sun, stretching from the orbit of Jupiter to within the orbit of Mars. Launched in 2004, a year later the probe passed by Earth for the first gravity assist that flung it towards the orbit of Mars. Two years later, Rosetta grazed Mars, building up momentum, then swung by Earth for a second time, launching it deeper into space. The following year, Rosetta passed by asteroid Steins before swinging back for a third gravity assist from Earth. And in 2010, Rosetta passed by asteroid Lutetia. Going into hibernation, Rosetta continued its parabolic trajectory towards its final destination. 4 years later, Rosetta emerged from its cold sleep as it crossed paths with the comet, a circuitous flight indeed. The spacecraft then embarked on a series of maneuvers that took it on 2 successive triangular paths. Its trajectory was fine-tuned with thruster burns until it closed in to within about 30 kilometers of the comet, where the spacecraft entered actual orbit around it. Rosetta remained with the comet, delivering it cargo, then conducting science observations as it swung about the Sun, then concluded with a gentle impact on the comet's surface in 2015.
We're going to refine our ideas of what the comet is, where the comet came from, and encapsulate that within our ideas of how the solar system formed. And the complexity of the data set that we have also allows us to be more complex in our ideas and our theories. And that is the beauty of Rosetta, and we're starting to see that happening now, that we're really able to hone down our ideas of how the comet formed, how that fits in the evolution of the solar system, and that's going to continue.
The Ulysses spacecraft had to leave the ecliptic plane of the solar system to study the polar regions of the Sun. Accordingly, it needed to change its orbital inclination. This required a large change in heliocentric velocity, so a gravity assist maneuver around Jupiter was chosen. The giant planet's gravity bent the spacecraft's flight path southward, putting it into an orbit over and under the Sun's north and south poles. The ion-powered Dawn spacecraft took maneuvering a step further.
Dawn's the only spacecraft ever in more than 58 years of space exploration to orbit 2 extraterrestrial destinations, the last uncharted worlds in the inner solar system. And it not only allows us to get to these distant bodies, but once we're in orbit, we can maneuver extensively in order to get the best possible science that we can from the mission.
NASA's latest mission is underway. OSIRIS-REx is the agency's first attempt at intercepting and touching down on an asteroid. No ordinary asteroid either. Bennu is its name. Orbiting the Sun very closely to Earth's orbit, it has been deemed a possible impact threat in the coming centuries. NASA intends to take a sample of the asteroid and return it to Earth for further study, and possibly help form plans to redirect Bennu. To match the orbit, OSIRIS-REx made a very close swing by the Earth a year after launch. It passed by the South Pole to change its orbital inclination several degrees to match that of Bennu. Once matching orbits, OSIRIS-REx must perform a series of braking maneuvers to match velocity and enter an orbit around the asteroid. After mapping and studying the body, OSIRIS-REx will drop down to the surface and collect a sample of material. With some clever robotics, the sample return capsule will be delivered back to Earth.
Well, the thing that is so intriguing to me about asteroids is that they really are time capsules. They actually are samples of what the solar system was like billions of years ago. Asteroids are small bodies that never got made into something big like a planet. So anything that got made into a planet got melted down, got changed. There were lots of things that went on. Asteroids are pristine. Nothing really altered them for billions of years. So when you go out and you take a sample of an asteroid, you have in your hands a real sample of what the solar system was like billions of years ago. What were the conditions? What was the chemistry like? What can you learn about the formation of our own planet and ourselves by looking at what the solar system was like billions of years ago? And this sample is incredibly scientifically important. I think that people will be studying it for generations to come.
The Juno space vehicle was launched in August 2011. In 2012, at perihelion, the craft performed some maneuvers out beyond Mars orbit and arched back towards Earth for a kick in speed and direction. In October 2013, it flew by Earth a mere 500 kilometers from the surface. This slingshot sent it on a 3-year journey directly towards an interception with Jupiter.
Jupiter orbit insertion is probably one of the most important things in the entire mission, and it's because that changes us from being in orbit around the Sun to being captured in orbit around Jupiter. And if you're not in orbit around Jupiter, you can't do the science we want to do. we're learning now is even in other solar systems, they don't always all have a monster like Jupiter. And many people think, boy, you almost need a Jupiter to have an Earth maybe. Jupiter played a big, important role. But its environment, everything about it is extreme. It's a planet on steroids, right? It is the most extreme in every way it can be. So it has the strongest magnetic field, the strongest gravity field. It has the most harsh radiation. It's spinning super fast. I mean, everything about it is this extreme environment.
The Juno mission is unique because it's the first time that we've ever gone in a polar orbit, which goes from pole to pole, over the North Pole, through periapsis, and under the South Pole. All the other missions we've done and all the observations we made from Earth were made from the equator. And you don't see the poles very well if you're sitting on the equator. Yes, this is the first time we get the first clear, unobstructed view of what the aurora looks like and what the polar phenomena looks like. And at the same time, we're flying through the magnetosphere right above the aurora, so we can sample in situ the charged particles that are precipitating down magnetic field lines, the guys that are exciting the emissions that we see. This is the first time we've ever been able to do that.
The 6.7-year, 5 billion kilometer transit journey of the Cassini probe was slightly longer than the direct Hohmann transfer. The mass of the Cassini spacecraft was such that even with the Titan IV launch vehicle, Cassini needed added help to reach Saturn. So, to gain momentum, the Cassini mission included several gravitational slingshot maneuvers. 2 flyby passes of Venus, 1 of the Earth, and then 1 from the mighty planet Jupiter. The Cassini orbiter then spent several years orbiting and maneuvering around the planet and its moons, finally diving through the inner rings of the planet.
When we go into the proximal orbits between the rings and the planet, we've never been there before, and we'll be a little bit more concerned. Here, we've actually been closer to these rings, the Janus Epimetheus ring and the F ring, when we went into orbit around Saturn. So this is not unexplored territory at this point. The nice thing about this, though, is that we've got a much better viewing angle of the rings because of the sun this time around.
And eventually into its atmosphere. The New Horizons spacecraft had further to go than Cassini, but being far less massive a probe, it was able to be launched directly towards Jupiter. The spacecraft was launched in 2006 and made its way to Jupiter. Its closest approach happened only a year after its departure, at a distance of 2.3 million kilometers. The flyby provided a gravity assist that increased the probe's speed. It also allowed for a general test of New Horizons' scientific capabilities, returning data about the planet's atmosphere, moons, and magnetosphere. Most of the post-Jupiter voyage was spent in hibernation mode to preserve onboard systems. In 2014, New Horizons was brought back online for the Pluto encounter. It flew 12,500 kilometers above the surface of Pluto, making it the first spacecraft to explore the dwarf planet, and then on into the Kuiper Belt towards its next target, a Kuiper Belt object most likely composed of frozen volatiles or ice, such as methane, ammonia, and water. A future probe to return to Jupiter's moons is destined for another multi-year journey. JUICE, to be launched in 2022, will embark upon a 7-year odyssey, taking the spacecraft via an Earth swing-by, then to Venus, back to Earth with a slingshot to Mars, then back to Earth for a final kick, direct to Jupiter. Heading outward bound is one thing, but launching payloads inward towards the Sun is another set of problems. For example, the Bepi-Colombo mission to Mercury, launching this year, will require 9 gravity assist maneuvers. After launch, a 2-year journey using ion propulsion will bring it back to Earth for a kick towards Venus, followed a year later by another flyby of Venus, sending it closer towards the orbit of Mercury. In the following 4 years, the spacecraft will pass by Mercury, tightening its heliocentric orbit until it can match Mercury's speed, and with the aid of chemical rocket motors, insert itself into that planet's orbit in 2025.
So studying Mercury is crucial to better understand the formation of our solar system, how Earth is formed and evolved, and where we are coming from. So Mercury is in a way a missing piece in the big puzzle of the formation of the solar system, and a crucial end member because it's close to the Sun, and if you want to get this full picture, you have to look at the planet close to the Sun, as we also did in past missions that we were looking at the comets or planets further out.
Our main target is the environment around the Mercury, especially the interaction between the solar wind and the Mercury magnetosphere.
Mercury is 3 times closer to the Sun, and therefore the radiation or the heat which we are getting from Mercury is 10 times higher. So everything which we had to develop had to withstand the higher temperatures, but also the higher radiation doses which we got from the solar wind. And for that we need special insulation of our spacecraft, special materials to be developed for the antenna, for the solar panels. And that was a very big challenge for the mission in itself.
There are 2 more missions in the next year or 2 that will travel further inward than Mercury: ESA's Solar Orbiter and NASA's Parker Solar Probe. Planned for a 2018-19 launch, ESA's Solar Orbiter will take several gravity assists from Earth and Venus to enter an elliptical orbit resonant with Venus, so that subsequent gravity assists will raise the orbital inclination, resulting in an operational orbit of 25 degrees inclined to the ecliptic plane and increasing to 34 degrees, making direct viewing of the Sun's polar regions possible. During the nominal 7-year mission, the main scientific activity will take place during the near-Sun encounter and high-latitude parts of each orbit, with different science goals planned for each orbit. Together with NASA's Parker Solar Probe mission, it's hoped it will revolutionize our understanding of the Sun, where changing conditions can percolate out into the solar system, affecting Earth and other worlds. Launch window is late 2018. It will use Venus gravity assists during 7 flybys over nearly 7 years to gradually bring its orbit closer to the Sun. At closest approach, the Parker Solar Probe will travel around the Sun at approximately 700,000 kilometers an hour. Some 10 times closer than Mercury, the front of Parker Solar Probe's solar shield faces temperatures approaching 1,377 degrees Celsius. It will travel through the Sun's atmosphere, closer to the surface than any spacecraft before it, facing brutal heat and radiation conditions, and ultimately providing humanity with the closest ever observations of a star. Flying into the outermost part of the Sun's atmosphere, known as the corona, for the first time, Parker's Solar Probe will employ a combination of in situ measurements and imaging to revolutionize our understanding of the corona, expand our knowledge of the origin and evolution of the solar wind, and explore what accelerates the solar wind as well as solar energetic particles. It will also make critical contributions to our ability to forecast changes in our space environment that affect life and technology on Earth. We have been observing our home for 40 years now. In the last 20 of those, we have focused intensely on planet Earth. With new technologies and capabilities, accumulating a massive data that is now revealing a complex and ever-changing living planet. They've been watching us from space for the last 2 decades in high-resolution detail, watching our every move. The clouds and aerosols, winds and hurricanes, forests and cities, droughts and floods, the ocean currents and plankton, life in the ocean and on land. Land cover, aerosols, chlorophyll concentrations, wave heights, ozone concentrations, atmospheric moisture, the human footprint, sea level change, and temperatures and moisture in the soil. Now scientists have a high-definition data set spanning 2 decades to study and to learn from.
Well, NASA has a fleet of satellites that are always measuring Earth. They're looking at land, oceans, atmospheres, ice all together. The particular visualization represents the measurement of all life on Earth over 20 years. I personally find it mesmerizing. You're watching the Earth breathe here. The seasons are changing, ice is coming in and retreating. You can see the forests on land in green, expanding and contracting. You can see the deserts moving to the ocean. You can see biological deserts in the centers of the ocean, represented by blues and purples. And then as you look farther north in the Atlantic or towards Antarctica, you can see these greens and yellows. Explosion of life in the ocean, just like on land in the spring and summer. incredible.
What we see for the first time is how the oceans and the land behave at the same time through time for 20 years. We've never had data like these before. Half of our photosynthesis occurs in the oceans and the other half on land. And having these data to show both at the same time, day after day, month after month, year after year for 20 years, is a great tool to study life on Earth. NASA has observed many aspects of the coupled land-ocean atmosphere system and how they interact. For example, we see that with warmer surface temperatures, the growing season is getting longer at higher northern latitudes, and spring is coming earlier. With satellite data, we're able to map this continuously across the Earth's surface and across the United States and across Alaska. Before that time, you had to rely where you had weather stations, and so you had points here, points there, but you never had continuous data like these. So using these data, we can look over very large areas and see regional effects, and sometimes these effects are positive in that nothing bad has happened. So it's only with these data we're able to do this over all these areas at the same time. And this is made possible by the use of Earth viewing satellites, which orbit the Earth day after day, month after month, year after year. And these data are the basis for saying these things about Earth with confidence because we measure them.
The view from space is opened our eyes to so many different things. You can see transitions from La Nina to El Nino, represented by huge blooms of life across the Pacific Ocean at the equator, bigger and wider than the United States. You can see greening of the Arctic, you can see earlier summers, later winters, and you can see the emergence of harmful nuisance algae.
Charting the carbon dioxide cycle through the atmosphere, land and ocean is essential to understanding the environmental changes that man is driving. Higher carbon dioxide, or CO2, in the Earth's atmosphere appears as red and yellow, while lower than average CO2 is shown as blue. The pulsing of the data is due to the day-night cycle of plant photosynthesis. As CO2 is lifted away from the surface, it is rapidly spread around the world by high-altitude winds. CO2 builds up in the northern hemisphere winter when plants are dormant. By summer, photosynthesis draws massive amounts of CO2 out of the atmosphere, resulting in lower CO2 throughout the northern hemisphere. The growth and decay of vegetation in the northern lands causes the seasonal change in atmospheric CO2. Long term, however, it is human activity that is increasing overall CO2 levels.
So 2017 was the second warmest year ever recorded and the warmest non-El Nino year. That makes 5 of the warmest years ever recorded just since 2010. And NASA scientists have taken weather station data from over 6,000 stations, and we've connected the dots to understand how our Earth is changing. In this animation, you can see those warmer temperatures growing as we look at how much the high latitudes in places like Alaska have warmed since 1950. So across the globe, we're seeing a consistent trend towards warming, but with twice as much warming across the high latitudes like Alaska.
This rapid increase in overall global temperatures is clearly defined when satellite data is added to the model.
The ability to expand your senses into space, compress time, watch visualizations like these, see how the ecosystems of land, ocean, atmosphere, ice all interact, and then be able to rewind it and watch it again and again. It's amazing.
Ask any astronaut. When they look down at Earth, they see a single environment. No borders, no claims, just a single planet which we all have to rely on. With this data, scientists can check up on the health of the planet. One primary concern is the ozone layer.
So we know the Montreal Protocol was a huge success. This was signed in the late 1980s when scientists and policymakers from around the world gathered together to try to save the ozone layer.
The chemicals they regulated persist in the atmosphere for many decades. They thin the ozone layer and they create a seasonal hole over Antarctica. They basically take away part of our planet's natural sunscreen, and that increases the risk of skin cancer and damage to plants.
Scientists have projected the ozone hole will disappear almost completely by 2075, but several factors could delay that outcome.
There are some industrial compounds that are not banned by the Montreal Protocol, but as they enter the atmosphere, they will also hurt the ozone layer.
But the unregulated compounds have a short lifespan in the atmosphere, unlike the chlorofluorocarbons that were originally regulated. So they have a short-lived impact on ozone, and we don't think they'll delay recovery by more than a few years.
We projected by 2050, more than half of the ozone-depleting compounds in the atmosphere will come from long-lived substances banned by the protocol.
Because these compounds stay in the air for such a long time compared to the unregulated short-lived compounds, they will have a disproportionate and lingering impact on ozone. Any non-compliance with protocol can have significant consequences.
And the really big uncertainty in ozone layer recovery is climate change. There are many naturally produced ozone-depleting substances that are emitted by the oceans. And as the oceans continue to warm due to climate change, those emissions will increase, and that will further delay ozone recovery.
Scientists want to understand better how climate change will affect ozone recovery.
This is a hard problem. As a scientific community, we need to work on this major issue. We now have a powerful new tool to simulate atmosphere and its interaction with land and ocean to study this issue. And that's what we're going to do.
At the top of the world, however, the Arctic ice continues to shrink.
Sea ice is the ice that grows and melts within the Arctic Ocean. It grows in the wintertime when it gets cold and melts through the summertime. And so it doesn't raise sea level, but it's very important for the global climate system because the ice is very bright and reflective, reflects a lot of the sun's energy that comes in during the summertime and helps keep the Arctic cooler. It's like a refrigerator for the global climate system by keeping the globe cooler than it normally would be without sea ice. And as we lose the ice, it's like we're opening the refrigerator door and not cooling things as efficiently as we used to.
Constant observation since the 70s lets us see a trend.
The Arctic sea ice has been changing quite rapidly. We've seen a decline over 35 plus years of a record. The last 15 years particularly, it's been accelerating. So really, it's become a matter of when, not if, we lose the Arctic sea ice because we have a lot of warmth in the Arctic. It's going to continue to warm. We're going to continue to melt sea ice. There's uncertainty as to exactly when that will happen, but sometime in the not too distant future, faster than we used to think, the Arctic Ocean will be substantially ice-free by the end of summer. Arctic sea ice is not the only place we're seeing big changes. We're also seeing big changes in Greenland, which is the big mass of ice on top of the continent, and we're seeing more and more melt. We're seeing ice calving off as icebergs, so we're seeing big masses of ice loss over the last several years. That means that ice is going into the ocean, that's raising sea level, so that's going to have big impacts down the road as we continue to lose more and more ice from Greenland.
Ancient air bubbles trapped in ice enable us to step back in time and see what Earth's atmosphere and climate were like in the distant past. Today we stand on the threshold of a new geologic era which some term the Anthropocene, where the climate is very different to the one our ancestors knew.
we can see that a warmer world means that there's an impact for warming temperatures in the Arctic, melting sea ice. That sea ice leads to larger sea level rise. So NASA scientists are on the ground in airplanes and using our satellite data to understand how what starts in the Arctic doesn't actually stay in the Arctic.
The hope is that all this data collection will mean that real-world problems can be reassessed and new angles explored. A case in point, dolphin and whale stranding. Could this accumulated satellite data help address the problem? Cape Cod in the US state of Massachusetts is home to one of the most frequent marine mammal stranding sites in the world.
If we can get there quickly and provide supportive care, they have a much better prognosis in terms of survival.
Scientists know very little about why these mammals strand, and only a quick and efficient response in these events will save lives. Katie Moore works on the front line and has fine-tuned rescue efforts.
If we can develop an algorithm that pieces together the different variables that may be causing mass strandings or driving mass strandings, then we have the ability to then prevent them. We can have teams that are out on the shore looking for animals in those hot spots, knowing that all those variables have come together and this is the likely point in time where we're likely to see it. But we can also have teams ready to respond so that if they do strand, we're there that much faster and more animals will survive the event.
Marine biologists from the US Bureau of Ocean Energy Management were also looking at this problem.
For the large proportion of these strandings, the animals are across the ages, in pretty good health, and there's no really immediate evidence as to why they actually strand.
One possibility is geomagnetic perception, the ability to navigate using Earth's magnetic field, which is believed to be used by marine mammals. Could changes in the magnetic field confuse the animal? Geomagnetic pulses or storms can be caused by space weather.
Geomagnetic perception is one of the theories, and I thought, well, if a magnetometer can pick it up, maybe the animals actually can pick it up.
Dr. Reed consulted with NASA at the Goddard Space Flight Center.
The coolest thing was that we realized that nobody had really taken a cold, hard data science analysis look at the problems.
What we were trying to look at here was if there was a potential driver or relationship or correlation between the occurrence of mass strandings and any solar activity.
The data that we have correlated or analyzed so far is information about the local geomagnetic conditions. We have long data records from geophysical observatories of the local geomagnetic field variations and marine mammal stranding.
Their analysis was inconclusive. They needed more data from other environmental conditions.
Easy fix correlation between a geomagnetic pulse and, a stranding doesn't seem to be very evident, but what it does show is that there are multiple variables involved in this equation, and that the geomagnetic storms could just be one very small part of it. Significant still, but it looks like there are multiple oceanographic and environmental elements.
With more data in hand, it was time to expand the team. They recruited statisticians and the expertise of NASA Earth Science data analyst and oceanographer Erdem Karakolu.
A data set, no matter its shape or content, always has a story to tell. Trying to figure out how different data are connected, I think, require a wide diversity of skills and background knowledge.
For example, I'll be explaining how a mass stranding occurs and how we respond to try and understand why I'm presenting the data in a certain way. And my colleagues from NASA will look at me and ask questions that I wouldn't think to ask because I take for granted my understanding, and they're coming at it from a totally new angle with no background.
These data sets may reveal a pattern, allowing scientists to predict the likelihood and location of mass stranding before it happens.
We've really just sort of slowly peeled the first layer of this onion back. And I think that there's so many more layers that still need to be addressed and looked at. And I hope that we can actually find additional collaborators, additional funding partners to really bring all the data that's really available to really give this the study and the scrutiny that it deserves.
And we are also going to make all these data sets available to the entire scientific community so that we can utilize the entire scientific community to take an attack and approach this problem.
I think that there will be other things to take and run with, get new ideas, maybe add more data. And I'm hoping also that will be a model for how projects can then be open to the wider public.
The ability to release animals after they've stranded is tremendous. When we do that, I mean, that's the best feeling in the world after all of that hard work.
Those questions that seem unanswerable, if you give them time and support and effort and put people on them, we can do amazing things.
Data from satellites reveals the interconnection between air, sea, and land. This is a visualization of three aerosols: dust, smoke, and sea salt. The Calypso satellite data reveals in 3D how dust from the arid Sahara Desert is lifted by the winds each year and transported nearly 5,000 kilometers across the Atlantic Ocean. Some of it settles in the Amazon basin, the largest rainforest on the planet. Sahara dust contains phosphorus, an important nutrient for plants. Calypso shows that on average, 182 million tons of dust leaves Africa each year. When the Sahel was dry, the dust transport to the Amazon in the next year would increase. When it was wet, dust transport would decrease. We can now track global precipitation, wind currents, cloud cover, and ocean temperature. Satellites have detected a shift in phytoplankton populations across the planet's 5 great ocean basins, showing the expansion of biological deserts where little life thrives. Diatoms are one of the most abundant types of marine phytoplankton, but a new 15-year-long NASA study reveals global populations have declined. Diatoms, like all phytoplankton, have chlorophyll, the same photosynthesizing pigment as plants. They occupy the surface of the ocean, where they harvest light from the sun. In large numbers, diatoms form colorful swirling blooms that can be seen from space. According to the study, significant decreases in populations, shown here in red, are mainly in the northern hemisphere.
Diatoms rely on nutrients such as nitrate, silicate, and iron to reach the surface layer where they live. What a study shows is that the availability of these nutrients has changed due to the way they cycle within the water column.
Diatoms occupy the surface area of the ocean called the mixed layer. Nutrients collect on the ocean floor and are cycled up to this layer. Various physical forces can cause the depth of the mixed layer to become shallower, so that fewer nutrients reach the diatoms. Without these, their populations decline. This map shows areas on the globe where the depth of the mixed layer shallowed.
It's hard to pinpoint exactly why this change have happened. Things like wind, circulation, and temperature can affect the way these nutrients are brought to the surface layer. We hope a longer study can yield more information on whether these changes are in fact a trend or variability.
Next-generation satellites are reaching orbit now to continue this important work. They will collect data, maintain observation continuity, and allow scientists to track the changes in our environment. They can then model dynamic simulations to better understand this unique planet and the myriad of life forms that rely on it. Space is vast, yet collisions are commonplace. Gas and dust electrostatically flock together. Gravity takes over, coalescing grains into rocks, rocks into boulders, then asteroids colliding again and again, striking planets and each other. Stars collide, creating monsters of light and energy. Even galaxies collide over millions of years. Space is a rough place to be. That peaceful night sky cloaks a hidden danger. It might appear bejeweled, docile, and permanent, but if you look closely, you can see things happening, violent things. Stars engulfing planets and each other, protoplanets colliding, explosions rippling through gas clouds, triggering the birth of young stars, black holes devouring everything in their path. Closer to home, a more immediate danger is the debris from the creation of our solar system, spinning about in a heliocentric orbit just waiting to bang into something like Earth. Collision avoidance is the name of the game, and we now have the technology to do something about it.
Catalina Sky Survey and other survey programs are really sort of the start of the whole planetary protection ecosystem. It starts with discovery, goes on to follow-up and characterization, impact risk analysis, mitigation studies, but you can't follow up and you can't characterize and you can't calculate the impact risk of something you don't discover. In order to find a near-Earth asteroid, we take 4 images of a patch of sky separated by about 5 minutes.
And we take those 4 images and we blink them really fast, and it creates this little animation. So we can see that the stars in the background are static, as they should be. And if there's anything that's moving, it'll pop out.
And our software compares those images and identifies things that are not moving, which are stars, and removes those, identifies things that are transient from frame to frame, and tries to link those up.
We've probably seen about 1 million asteroids in the last 7 years that the PanSARS has been operating. It's like picking a needle out of a haystack. We're looking for distinctive motion, and when we see distinctive motion in asteroids, we report them to the Minor Planet Center. The Minor Planet Center is the sort of world clearinghouse for near-Earth asteroids.
The Center for NEO Studies takes the observations from the Minor Planet Center and computes the high-precision orbits that we use to make predictions. CNEOS is also kind of an early warning system for newly discovered asteroids. We take the early data and we compute whether or not that asteroid could hit the Earth. If there's a chance, we'll send out an early warning, an alert for follow-up observations so that we can get more data, and then we would know perhaps whether it can hit the Earth or not.
Asteroid impacts are a fact of life. The Earth has been impacted by asteroids continually through its history.
We saw in 2013 in Russia a fairly small, by the standards of what we're finding, asteroid did hit the Earth. I feel a little bit like a guardian of the planet and doing my bit to try to protect people. It is a long-term process. It's going to take many, many years to find all of the dangerous asteroids.
The goal is to find near-Earth asteroids before they find us.
Having the right tools helps us look further away in greater detail. The Hubble Space Telescope was one such tool that was able to capture the first spectacular impact seen in our solar system. The Shoemaker-Levy 9 cometary fragments which struck Jupiter, leaving a surprising impression. Even more remarkable was the recent arrival of an interstellar object.
It was a special day when this object was first discovered. We have been waiting for the discovery of an interstellar object for decades, basically.
Well, when I first heard about this interstellar object, it was very exciting just from a scientific point of view that finally there's been an actual observation of such an object.
This object is simply a piece of another solar system that was expelled, and it has been traveling through interstellar space for hundreds of millions of years, billions of years, we don't know.
A number of our survey projects and other observatories immediately turned their telescopes to take observations of this object. From the observations we have so far, it looks like it's a very elongated object, maybe about a quarter mile in length.
We think this object, 2017 U1, is very long, perhaps 400 meters or so long, and very narrow, skinny, perhaps maybe 40 meters or so in the other dimensions. That's a very unusual shape. We don't see that in our solar system. None of the asteroids in our solar system look like that. So it's very puzzling how it could have obtained this shape.
We also see that it's very reddish in color, which indicates that it's been possibly in space a long time and irradiated by not only the light from our sun, but other suns as well.
Well, there's still quite a bit to learn about this interstellar object and limited time because it's on its way out of the solar system.
It's fading very fast. It's a relatively small object, so it's very dim. But we are continuing to try to use NASA assets like the Hubble Space Telescope and Spitzer to take observations to determine more about its size and composition.
NASA's Planetary Defense Coordination Office has a near-Earth object observations program which funds efforts that survey the skies to look for near-Earth asteroids and to calculate their orbits and their trajectories and to determine if any of them might pose a hazard to Earth. And as part of doing that, some amazing discoveries can happen, and the discovery of this interstellar object was one of them.
As our observational capabilities improve, Pan-STARRS has been getting better, other surveys have been getting better. There are a new generation surveys that will come online. We will be detecting more of these in the future.
New observatories are being constructed. To be launched in the coming year, the James Webb Telescope will orbit at Earth's L2 Lagrange point 1.5 million miles from Earth, away from the Sun. Its low-temperature sensors will be shielded from the Sun, Earth and Moon. There are also 3 new ground-based observatories underway. A multinational project being built in Hawaii, the 30-meter telescope, or TMT, will use 492 hexagonal elements, each about 1.44 meters, to construct the single primary mirror of 30 meters diameter. The secondary mirror will be 3.1 meters in diameter. The largest of all will be Europe's Extremely Large Telescope, or ELT. The primary mirror consists of 798 segments, each 1.4 meters wide, but only 50 millimeters thick, with a light collecting area of 978 square meters. The optical design calls for an immense secondary mirror, 4 meters in diameter, bigger than the primary mirrors of any of ESO's telescopes at La Silla. Then there is the giant Magellan telescope, currently under construction in the Chilean Andes, which will be ready by 2022. It consists of 7 8.4 meter diameter mirrors, making a total effective aperture of 24.5 meters. Housed in a rotating 22-story high building, it will produce images 10 times sharper than Hubble, with a total collection area of 368 square meters.
This is a project that we began in 2003. It was a small group of U.S. institutions and has now grown to an international project that includes Australia, Korea, Chile, and most recently, Brazil. The next steps as we launch construction of this telescope are to build the mount, the steel mount that will hold the mirrors for the telescope, to build the enclosure, which is a 22-story building that has to rotate to allow you to move to different parts of the sky as you're looking out with the telescope.
It's a new epoch in the field of astronomy. It's a new epoch for cosmology, astrophysics, and the history of the universe. And so we'll be able to see things further and fainter than anyone has ever seen before.
And it just takes us to that next level of technical capability, and these technical leaps are what enable new discoveries.
The first 4 giant mirrors for Magellan have been manufactured. Number 5 is underway, as is construction at the site in the Chilean Andes.
GMT is really an exciting thing because we know that over the last 400 years that telescopes have gotten bigger, and that has allowed us to see things with better detail and to see fainter things and to figure out what the history of the universe has been. Our technology for doing this is getting better and better. We're able to build big mirrors, and we know how to do this. We know how to build GMT. We know how to build its individual mirrors and put them together. We know that when you build a telescope view, and the GMT will have a view that is 10 times sharper than the Hubble Space Telescope. And when you build a telescope that collects more light, and the GMT will collect 100 times as much light as the Hubble Space Telescope does, that you are going to be able to do things that we can imagine and set out as our goals, to look at the history of the universe, how things have changed, find out more about the dark energy and the dark matter. Those are things that we know you can do. But I think the really exciting things will be things that we haven't yet thought of, that the new questions that will come. The other part that's really interesting about a big telescope on the ground is that you can change it. That is, you can change the instrument. So I think that even when we build the telescope, that won't be its final form. Those instruments will eventually be replaced by better ones that use the technology that's developed over the period from now to then. We know that the universe has changed from a very homogeneous kind of goo at the time of the Big Bang into a highly differentiated world where there are planets, stars, galaxies, clusters of galaxies. The universe has gotten kind of interesting and complicated through the action of gravity over time. We'd like to see how that works. And by looking at what happened long ago, which means looking at very distant, very faint galaxies, and looking in detail, which means having the resolution to kind of really see what's going on.
No doubt revealing cosmic collisions far back in time and space. Not as close as the asteroid field, but still in our neighborhood, are other phenomena colliding in space. Out beyond the edge of our galaxy, the Milky Way is a cloud of hydrogen gas called Smith's Cloud, after its 1963 discoverer, Gale Smith. It is traveling at 312 kilometers per second and is about to collide into the Perseus arm of our galaxy. Well, in 27 million years or so. It was believed to have been ejected from the Milky Way some 70 million years ago. Why is still not known, but when it collides with the galactic arm, it will trigger a brilliant burst of star formation with enough gas to produce over 2 million stars. Another major event to occur soon is in the heart of our galaxy, where a supermassive black hole resides. This black hole's mass is a hefty 4 million times that of the Sun. ESO telescopes have been tracking the motion of stars around the giant black hole for 20 years. Although huge, it is currently supplied with little material and is not shining brightly. But that is about to change. Recently, they have discovered a cloud of gas traveling towards the gravity sinkhole on a collision course.
The cloud consists mainly of hydrogen gas which we see anyhow in the galactic center all over the place. This particular cloud weighs more or less 3 times the mass of Earth, so it's a rather small and tiny blob only, but it glows very brightly in the light of the stars which are surrounding the cloud.
We really don't know where the cloud came from, but we do know that most of the material which is currently flowing into the galactic center black hole comes from stellar winds, material which is ejected by nearby stars. And could be that this particular cloud also was coming from a star ejecting material, but happened to produce a very compact and directed right at the black hole. Well, the next few years will be really fantastic and exciting because we are probing new territory. Here this cloud comes in, gets disrupted, but now it will begin to interact with the hot gas right around the black hole. We have never seen this before. We expect it gets hotter. It may even start emitting X-rays, very hard radiation, and then it gets disrupted, and then in the end we expect it to fall into the black hole once it's sort of going through all of this churning.
As the astronomers watched, the cloud has been picking up pace as it gets closer to the giant black hole. Its speed has doubled in the last 7 years, and it is now speeding towards the black hole at more than 8 million kilometers an hour. The astronomers have already seen the cloud's outer layers becoming more and more disrupted over the last few years as it approaches the black hole.
The black hole, imagine it sitting here, has a tremendous gravitational force, and the cloud, as it comes in, it will be elongated and stretched. It will become essentially like spaghetti. It will be elongated and falling into the black hole.
Observations of other massive black holes at the center of galaxies have revealed many varied phenomena. One galaxy's supermassive black hole is emitting a powerful outflow of material and, to the surprise of astronomers, is forming stars. Results from ESO's Very Large Telescope are the first confirmed observations of stars forming in this kind of extreme environment. The discovery has many consequences for understanding galaxy properties and evolution. Black holes at the centers of galaxies still hold many secrets. Galaxies are the building blocks of the universe. The giant galaxies we see today, even our own, were built up from many smaller galaxies, and construction isn't over. Today, full-grown galaxies approach and interact with each other. They may collide and eventually merge, growing larger and more influential. As the galaxies approach each other, the tug of gravity creates tides that distort their shapes. Stars and gas stream into new orbits. Sometimes they're completely ejected, trailing into the depths of intergalactic space. Clouds of gas are compressed in the chaos and ignite with intense rounds of new star formation. Computer simulations have been conducted and compared to actual images of galactic collisions, an uncanny resemblance. Because stars create most of the chemical elements, each galaxy has a particular chemical makeup. This makes identifying groups of stars from different galaxies easier. This infrared image of our sky shows our point of view of the Milky Way, 500 million stars. Most are in our galaxy, some belong to companion galaxies that orbit our Milky Way, and some are in between. Astronomers have discovered that some groups of stars belong to a different galaxy called the Sagittarius Dwarf Elliptical, and the Milky Way is cannibalizing it. As the dwarf galaxy passes through the Milky Way's disk, gravitational tides stretch the dwarf stars into long streams that wrap around the galaxy's orbit. For the dwarf, it's a fatal attraction. For the Milky Way, just another one of several similar events in its history. But something much bigger is headed our way. M31, the Andromeda Galaxy. This is the Milky Way's biggest neighbor, of roughly the same size, mass, and type, and it is speeding towards us. Astronomers say the crash will begin in about 2 billion years. Supercomputer simulation shows how the event may unfold over billions of years. The first path distorts the two great spirals. Stars are tossed into the intergalactic night like sparks thrown from a campfire, and our sun, complete with planets in tow, could be similarly ejected. Gravity will eventually merge Andromeda and the Milky Way into a bigger single entity. With a new generation of telescopes looking skyward, we are sure to discover more dangers lurking in the heavens, though fortunately for us, they are millions or billions of years in time and distance away. We know it's there, and we usually pay it little mind. Yet we notice it when it's not there. Gravity is the all-encompassing force keeping us on the ground, and the planets in their orbits. In space, we are merely cheating gravity, falling just as fast, but missing the ground, an orbit and so-called condition of microgravity. Now this fundamental universal force is slowly giving up its secrets. Live in a gravity field. So what happens when they spend extended time in the zero-G environment, and how can we utilize what we learn to help human beings?
This time is not so
This A310 0G aircraft is being used by the European Space Agency for research in conditions of microgravity. To obtain 0G, the plane must perform a series of parabolas. On each maneuver, people first experience almost 2 Gs, feeling twice their normal weight. When the aircraft reaches a specific point,
20, 30.
They inject the plane into the parabola. Everyone on board is then in microgravity.
It's now called out the angle, it's 40 degrees at 50.
Injection.
Injection, that is weightlessness. Here I go. The scientists have 20 seconds of weightlessness to do their experiments behind me. But there will be 30 of these parabolas. So they have plenty of time, 10 minutes in fact,
20.
to do
30.
their experiments. Time to get down now, because there will be a nasty thud. There we go.
There are 12 experiments on this flight, including 6 by students as part of ESA's Flying Thesis program. The experiments cover everything from fundamental physics and neuroscience to psychology, looking at body image and perception. This experiment is examining the effect of microgravity on the brain. That's important for astronauts doing long-duration stays on the ISS, but there are also wider applications.
We are also interested in people with diseases, for example, Alzheimer's disease or dementia. If we know the mechanisms which are linked of a reduction of cognitive performance and brain activity and where that comes from, we might be able to better design strategies to then help these people.
Inside here is a pulsating heat pipe, potentially a new way of managing the thermal conditions of satellites or components on board the ISS. The copper pipe, seen here showing the flow of a condensed vapor, also has a section made of sapphire that is transparent to visible and infrared radiation.
In this experiment, we are using the infrared camera of the European Space Agency. It's a new camera, high-speed infrared camera, that will be used also on the International Space Station for the next experiment.
After each parabola, there is another 20 seconds of 2G as the plane pulls out to level flight. A few minutes later, the next parabola begins. In between each one, scientists must quickly reset their experiments and prepare for the next bout of microgravity.
This is the only microgravity platform where the scientists get to interact with their own experiment while it is in zero gravity. Rather than doing it by remote on a robotic capsule or sounding rocket, or on the ISS, it's humans, of course, but then it's astronauts doing it, and they can't possibly be as in tune with the scientific needs as the scientists themselves. So this is the only platform that really allows that kind of access, and as such, it's unique.
In the final few parabolas, everyone works hard to finish their science. For the German Mars Society experiment, however, there's only one shot to get this right, as it involves testing the initial deployment of a densely packed balloon that they hope, one day, will carry instruments for studying Mars's atmosphere. Whether it's preparing for Mars or helping life on board the space station and on Earth, the zero-G plane offers a unique environment for research and the closest conditions possible to being in space. Of course, the ISS is the ideal place to experiment with gravity, or the lack of it. Many experiments are conducted by the crew every day, with new experiments being sent up to the crews in cargo and crew capsules.
Now, you are free to set up as you want. This is just...
Fundamental questions are still to be explained. Most fundamental of all, what is gravity? How can such a weak force dominate the entire universe? How does it keep moons and planets in orbit? It affects everything, no matter what its mass may be. A leaf will fall as fast as a handful of nuts and bolts in vacuum, as tested on the lunar surface many years earlier by Apollo astronauts. It was this man who explained the force of gravity in the space-time continuum early in the 20th century. He theorized that gravitational waves were oscillations in the fabric of space-time, moving at the speed of light and caused by the acceleration of massive objects.
Gravitational waves were predicted by Einstein almost 100 years ago.
A gravitational wave is a ripple in the fabric of space and time. It's produced somewhere in the distant universe and travels across the universe.
When any massive object moves, it's changing the nature of space-time. That's what Einstein told us.
So you have a motion that stretches space in one direction and compresses space in the other direction.
Nobody really believed at the time of the prediction that you could ever detect them because the size of the effect is so small.
It would take multiple massive detectors around the world to sense such a small effect passing through the Earth. Question: how do you detect gravitational waves? Answer: with a Michelson interferometer. This is the GO600 in Germany. Laser light is split and sent along different paths in a vacuum, the longer the better, then reflected back on mirrors suspended on glass threads, completely isolated from any earthly vibrations. The laser light is then brought back together and the interference patterns of the two beams compared. The sensitivity required is astounding.
We literally look for changes in the space-time distance in our instruments as the gravitational wave goes by.
And the gravitational wave pushes them together and apart by 1/1000th the diameter of the nucleus of an atom. No wonder it's taken so long to pull this off.
The first detection was made by LIGO, two detectors a continent apart.
We have observed gravitational waves from two black holes forming a larger black hole.
They're moving at the velocity of light, damn near that velocity. 30 solar masses moving that fast. I mean, they're putting out incredible amounts of energy.
And when they collide with one another, they produce a bigger black hole, but they also produce gravitational waves. And in that process, about 3 solar masses just disappears and goes into gravitational waves.
September 2015 confirmed Einstein's vision of the waves and allowed a fascinating and unique view into the dark side of the cosmos, creating a new science, gravitational wave astronomy. Gravitational waves carry information that you can't obtain any other way. Massive events like a supernova, 2 neutron stars colliding, even the universe creating Big Bang itself, have all produced gravitational waves. These can now be detected, adding pieces to the jigsaw picture of nature and the forces that define space-time. Barely 2 years later, another scientific milestone was reached. Astronomers using a fleet of ESO telescopes have observed a visible counterpart to gravitational waves for the first time, a kilonova from merging neutron stars. August 2017, the LIGO facilities, in collaboration with their European counterparts dubbed Virgo, together detected gravitational waves rippling through the fabric of space-time. Just 2 seconds later, 2 space telescopes from ESA and NASA detected a short gamma-ray burst coming from the same general area of the sky. This coincidence had never been seen before. Astronomers hoped this was not just a coincidence, but another indicator of this cataclysmic event, 2 neutron stars combining in an explosive merger. If scientists were right, then a visible light counterpart known as a kilonova would be expected to follow, revealing the exact location of the source of gravitational and gamma rays. The hunt was on. ESO and ESO partner telescopes in Chile joined other observatories to search for a new light source. They were looking for a needle in a haystack, a faint new glimmer amid millions of stars. But amazingly, they found it just a few hours later. in the galaxy NGC 4993, 130 million light years from Earth. Neutron star mergers are the furnaces where most of the chemical elements heavier than iron are forged. The kilonova, an event 1,000 times brighter than a typical nova, spreads the newly formed elements, including gold, platinum, and uranium, into the surrounding space. Such an explosion had never been confirmed before, but here was one that could be studied in great detail. The ESO observations revealed an extraordinary and rapidly changing event, closely mirroring theory. Heavy radioactive elements were shot into space at 1/5 the speed of light. In just a matter of days, the kilonova's color changed rapidly from blue to red, faster than any other observed stellar explosion. This event marks the start of a new era of multi-messenger astronomy. For the first time in history, we can now combine light signals with gravitational waves, providing a totally new way to probe the universe. The advancement of gravitational wave detection didn't stop there. Talented engineers and scientists set about developing even more sensitive detectors that could be mounted in space, free of nagging earthly vibration and detector size limitations.
5, 4, 3, 2, 1, top, allumage et décollage de VV06.
A proof of concept mission, the Laser Interferometer Space Antenna, or LISA Pathfinder, was launched to test the feasibility of a space-based gravity detector. LISA Pathfinder was launched from Kourou, French Guiana, aboard a Vega launcher into a slightly elliptical parking orbit. Using its own propulsion module, it progressively expanded its Earth orbit over a period of 2 weeks before the cruise phase to its operational orbit at the first Sun-Earth Lagrange point, L1, 1.5 million kilometers from Earth towards the Sun. The science package was built around 2 identical gold and platinum cubes, each floating free in a vacuum. They act both as mirrors for the interferometer and as inertial references for the drag-free control system. A disturbance reduction system, or DRS, was supplied by NASA and consisted of 2 clusters of colloidal micropropulsion thrusters and an electronic unit containing a computer with associated drag-free control software.
So to me, the highlight of LISA Pathfinder is the very first day we turned it on, because we didn't expect the performance to be as good. We thought we would be close to what we had to do, and then we would improve it. We would think about what we have to do, we'd fix things, and it would get better. On day number one, it met requirements. What it showed us is that this is a very complex type of instrument, but it's doable, and industry now have the experience in how to make a mission like LISA and LISA Pathfinder.
These signals are very, very tiny indeed, and we've been able to show with these test masses inside the LISA Pathfinder satellite that we would be able to see gravitational waves in the frequency band where we're interested in.
I think LISA Pathfinder is already demonstrated that it's possible actually to place two test masses in free fall in space with a residual relative acceleration at the level required for the future gravitational wave detector.
LISA Pathfinder confirmed the technology for a space-based gravitational wave detector even before the science operations began.
So a space-based detector like LISA is looking for low-frequency gravitational waves. And by low frequency, really we're talking about very big objects which are in motion. So we're looking at the centres of galaxies, the supermassive black holes at the centre of a galaxy, and when two galaxies merge, the two black holes eventually form one big entity. And it's in that merging of the two black holes is what we're picking up through LISA.
Proving this type of technology in situ is a big leap forward in detectors.
It has worked flawlessly, and our performance is better than we could ever have dreamt. Even on the very first day, we had met our requirements, and since then we've just made it better, and it's just wonderful to see how well this instrument is performing. The success of LISA Pathfinder demonstrates that we now know how to build a mission like LISA, and over the next months and years, that mission will now start to be in the design phase, leading to a launch in the late 2020s or 2030s. Gravity is the fundamental force of the universe. At the largest scales of talking about stars, galaxies, the universe, they're dominated by gravity. However, gravity does not get absorbed very well by matter. We're sitting here in a building, we're not floating off in space, we've got a building between us and the Earth. So gravity penetrates all matter. So for that reason, the gravity is passing through our detector, and it doesn't really dump any energy in the detector the way an electromagnetic telescope would pick up light. So we have to actually look at the ripples in space-time. We have to look at the effect of gravity over all of space.
And like other waves propagating through space, gravity waves too have various wavelengths or frequencies.
We need LISA because it's looking at a whole new part of the spectrum of gravitational waves. It's a whole new type of science we're doing. So with the LIGO detections, they're looking at objects that are roughly the size of the Sun, so anywhere from 1 to 100 times the mass of the Sun. And in their case, it was about 30 solar mass black holes which were orbiting each other. Whereas with LISA, we're looking at galaxies merging. So it's no longer stellar-like objects, it's now galactic objects. So things which are maybe 1 million times the mass of the Sun, the big black hole at the centre of galaxies. When galaxies merge together, eventually these black holes collide. And when that happens, it rips a universe apart. And we're looking for that universe vibrating from these merge of these big events. Something you can never ever do that on the ground. So LIGO will never be able to see the events that we see with LISA.
The LISA mission will consist of 3 satellites precisely positioned to each other in an Earth-trailing orbit. There they will connect to each other via laser beams, forming a single detector.
So the big difference between LISA and LISA Pathfinder is the length of the arm. So in LISA Pathfinder, we had 2 gold platinum cubes in our spacecraft, and they were separated by about 40 centimetres. Whereas in LISA, the little cubes are separated by 2.5 million kilometres. So to put that in perspective, that's about 6 times the distance to the moon. So it's a long, long way.
Work has begun on the LISA project. It will take over a decade to plan, design and build, then test the 3 spacecraft. When LISA launches in 2034, it will be able to detect gravitational waves from objects up to 100 times the mass of our Sun. The engineering challenges alone are daunting.
So the challenges of a mission like LISA or LISA Pathfinder is the fact that it's built with, I think we had 40 different companies from 14 different countries building aspects. And unlike some of the planetary missions or some of those astronomy missions where you have a camera and a telescope, our whole satellite is one instrument. And if we go to LISA, all 3 satellites form one instrument. So everything has to come together, it has to work, and that's what happened. You know, we had a very great collaboration within Europe, and when it all came together, it worked as an instrument on day one.
None of that would have been possible without Albert Einstein, LIGO, and the LISA Pathfinder. Its success has paved the way for a whole new window into the mysteries of our universe.
Gravitational waves allow us to see the dark side of the universe, the things which are not shining light, for example, black holes. So now we can actually go out there and we can really observe these things which we've got no other way to see. And also, their gravitational waves were predicted by Einstein, and this is one of the main pillars of general relativity. And with LIGO, and even better with LISA, we can really start to probe general relativity and see that is actually theory which governs the gravity of the universe.
The interface between Earth and space is the ionosphere, a region of rarefied gas and charged particles. It is very important for radio communications, radar, satellite signals, and global positioning. Yet we know so little about it, especially when it disrupts all these signals in a regular fashion. Too high for planes or balloons, it's up to satellites to study this rarefied region. We have become so reliant on radio signals bouncing off the upper atmosphere and beaming down from satellites that the ionosphere has become a critical part of our technology. From aircraft communications and radar to managing navigation of the world's shipping lanes and global positioning for fishing trawlers to locate their catch. GPS for the military, on the ground and in the air. Yet we know very little about this region of Earth's atmosphere. Critically, there are times when global positioning signals become unreliable. The satellite and radio signals twinkle in much the same way as bright stars appear to do at optical wavelengths. Irregularities in the ionosphere, referred to as ionospheric depletions or bubbles, span the hemispheres at the equator and are a major element of the low-latitude geospace region.
It's very important for us to understand the ionized portion of the atmosphere, the ionosphere, as well as the upper atmosphere, because that's where satellites are, low Earth orbiting satellites are orbiting in that region. Astronauts are exploring that region, as well as the communication and navigation signals travel through that region. And so when you have disruptions in the ionosphere and variability in the ionosphere, that can affect our navigation and communication systems.
The ionosphere lies some 40 to 600 miles above Earth's surface. The upper atmosphere and ionosphere change constantly in response to forces from above and below, including explosions on the Sun, intense upper atmosphere winds, and dynamic electric field changes. These irregularities form huge horseshoe arcs between hemispheres, with their apices centered on the magnetic equator. To learn more, NASA conducted a mission called CINDI, the Coupled Ion Neutral Dynamics Investigation. CINDI was designed to measure ionization of the upper atmosphere, including the behavior of the irregularities responsible for the GPS twinkling, which turned out to be quite surprising. The ionosphere becomes unstable shortly after the sun sets. As darkness falls, ionized atoms and molecules begin to recombine into a neutral state. During this transition period after sunset, irregularities are quite strong. As the night wears on, however, these irregularities were thought to fade and eventually vanish around midnight. Cindy found many irregularities around sunset, but they did not vanish around midnight. On the contrary, there was another peak in irregularities during the middle of the night. This second peak has appeared most pronounced from June through August. Scientists aren't sure yet why this second peak occurs or why it varies by season. The Cindy mission ended with the re-entry of the spacecraft into Earth's atmosphere. Researchers still had much to learn about the ionosphere and how it can affect GPS and other satellite systems. To understand the tug-of-war between Earth's atmosphere and the space environment, NASA created the ICON satellite.
So with the ICON mission, we're looking at the very upper levels of the Earth's atmosphere and the charged plasma environment that surrounds the Earth that we usually consider as the inner edge of space. So that region is called the ionosphere, and that's what gave us the name for the Ionospheric Connection Explorer. But really a lot of what is happening there is being driven by the winds and the composition of the Earth's atmosphere.
So these altitudes, the thermospheric altitudes that the ICON mission is investigating are typically too low for satellites to fly in and too high for weather balloons to get to, for example. So we need to use remote sensing techniques to get the information at the right altitudes. And the atmosphere actually helps us do it because there is something called an air glow. The atmosphere naturally just glows at those altitudes more during the day and less during the night, but it's always there. This air glow is always there. And by just looking at the color of this air glow, we can find out about the wind and the temperature, actually. So it's the atmosphere, in a way, is helping us to understand how it is behaving by sending out this air glow. And if we build the right instruments to look at particular aspects of the color of the air glow, we can get the information that we want.
So what ICON is trying to do is observe these two systems at the same time from one satellite. So it does that with 4 instruments, and broadly speaking, 3 of those are kind of camera instruments that look out at the Earth off on the horizon. And one of them measures the temperature and wind of that atmosphere. One of them measures the composition of the atmosphere. One of them is getting the plasma environment, this charged particle environment. And then there's a 4th instrument that measures the charged particles and their motion and things at the location of the spacecraft.
High-altitude wind shear is thought to be one of the factors for GPS twinkle.
It's just the movement of the atmosphere, same thing as we experience as wind down here, except for the winds are generally much faster up there, and there's very little atmosphere, so the pressure is very, very low. So those are the 2 major differences between what we think of when we say the word wind here and what we experience up there, or what the instrument sees up there.
ICON was placed aboard a Pegasus rocket and flown into the stratosphere under the belly of an orbital ATK aircraft. Once it is at the right altitude and heading, the rocket drops away, then ignites its main engine, carrying the spacecraft into orbit. Once in orbit, the spacecraft is commanded by scientists at Mission Operations Center at the Space Sciences Laboratory at UC Berkeley. ICON then began its study of the frontier of space, the dynamic zone where terrestrial weather from below meets space weather from above. In this region, the tenuous gases are anything but quiet, as a mix of neutral and charged particles travels through in giant winds. These winds can change on a wide variety of timescales, due to Earth's seasons, the day's heating and cooling, and incoming bursts of radiation from the Sun. To understand what drives the variability in the ionosphere is very complicated, a system that is driven by both terrestrial and space weather. A second satellite mission was needed, another suite of instruments in a higher orbit named GOLD. A first for NASA, GOLD was piggybacked on a commercial satellite.
The GOLD mission stands for Global Observations of Limb and Disk, and it's a very important mission for us to understand the upper atmosphere of the Earth, the thermosphere and ionosphere of the Earth. It is our first hosted science payload that NASA's flying on a commercial spacecraft. And so that is a new innovative way for us to do science that maximizes our private sector partnership as well.
GOLD will be sitting 22,000 miles above Earth, which means that it can see a whole half of the Earth, all of the Western Hemisphere. And it will be hovering over one particular point on Earth, watching the dynamics of the atmosphere play out below.
From geosynchronous orbit, GOLD can scan half the planet at a time.
I am excited about this mission because GOLD will be getting information about the upper atmosphere much faster than ever before, and will be able to look at effects that are more like the weather that we experience down here on Earth.
The two influences on the ionosphere are space weather and weather below, closer to the ground. Space weather is the realm of the Sun, coronal mass ejections affecting our magnetic field and showering us with energetic particles. The Sun's energy starts in its core, a giant fusion engine where hydrogen atoms are turned into helium atoms. The energy produced there moves up through the convection zone to the Sun's surface, the photosphere. Moving magnetic fields contribute extra energy along the way, bursting from the surface, emitting light and heat that is channeled by the Sun's magnetic field, generating the turbulent surface, including prominences, flares, and coronal mass ejections that spread out into the solar system.
Space weather is the field that studies how what's going on the Sun affects us here on the Earth in our near space environment and on the space environment on other planets.
These powerful bursts of energy travel outward toward the planets. This space weather, consisting of light and thermal radiation, includes high-speed solar wind and energetic particles which collide into planets orbiting the Sun. Earth has some defense, its magnetic field that deflects and absorbs much of the energy, distorting the magnetic field. Some energy is captured and follows the magnetic lines to the poles, generating auroras.
NASA hopes to achieve with the GOLD and ICON missions a better understanding of the near-Earth space that's so important for our global infrastructure.
To help predict space weather, many Sentinel satellites watch the sun closely. IRIS is one of them. It watches our star in ultraviolet wavelengths and is able to give us warnings of extreme space weather events approaching Earth. This space weather has a direct influence on our ionosphere. Another tool to watch both the solar weather and Earth's weather together is about to go into operation, replacing its aging predecessor. GOES-R is a next-generation weather satellite with the latest in technology. It will be 5 times faster, advanced resolution cameras giving greater coverage for hurricane tracking, real-time mapping of lightning, and improved solar flare monitoring. Almost by accident, the Fermi X-ray telescope in Earth's orbit discovered another source of gamma-ray particles coming from Earth. Under just the right conditions, lightning storms fire off some of the highest energy light naturally found on Earth, terrestrial gamma-ray flashes, or TGFs. Rising and falling snow and ice particles repeatedly collide, filling the cloud with electrical charge. Once the electric field is strong enough, a current flows and a lightning flash occurs. The flash produces an abrupt reconfiguration of the electric field. In some cases, a surge of electrons rushes towards the upper part of the storm at speeds nearly as fast as light. When deflected by air molecules, these accelerated electrons give off gamma rays, producing a TGF. Data from NASA's Fermi Gamma Ray Space Telescope suggest more than 1,000 TGFs occur each day all over the globe. Tropical storms far from land tend to generate less frequent lightning. Nevertheless, observations show they are surprisingly prolific producers of TGFs. Tropical storm Manuel made landfall just shy of hurricane strength. As it rapidly weakened, it produced 2 TGFs within 24 hours. More typically, TGFs are associated with the strengthening phase of a storm. As Typhoon Bolavin rapidly developed in 2012, thunderstorms nearly 500 miles from its center launched a TGF with 4 distinct pulses. So far, the record holder for TGS is the rapidly strengthening tropical wave that later gave birth to Hurricane Julio. It produced 4 TGFs within 100 minutes. A 5th followed the next day, with nothing further. For stronger storms like hurricanes and typhoons, TGFs are more common in the outer rain bands, which host the highest lightning flash rates in these storms. The findings provide new insights into the relationship between storm intensity, lightning frequency, and TGFs. This adds another important piece to the puzzle of our understanding of TGFs and how they are created in thunderstorms, the most powerful natural particle accelerators on planet Earth.
Ultimately, the science that we learn from Golden Icon will help us be able to predict the near-Earth environment that affects our communication and navigation signals and capability, but also how space weather affects the upper atmosphere, which can translate to effects on the ground in terms of our power systems and our navigation systems down below.
The march of technology must go on. ESA and the European Union can see the future of global positioning, and it is a growing market, with more and more technology requiring their services. The Galileo program is nearing completion with a total of 26 satellites orbiting at 22,000 kilometers. The penultimate launch of 4 Galileo satellites aboard an Ariane 5 will occur soon. As with all other Galileo satellites, these newest additions will fly in a medium Earth orbit. The last launch of 4 satellites will occur in the near future. Although the constellation is not yet complete, it has been in operation for almost a year since the European Commission announced initial services on the 15th of December 2016.
The completion of the constellation will take place in the summer of 2018, where we launched the last Ariane 5 with 4 satellites, which will bring the total up to 26 satellites. So we have at that moment 2 satellites in reserve, and we will then, after that, start putting some extra reserves in space in order to be prepared just in case.
These services were the first step towards full operational capability, and a first opportunity for the Galileo system to prove its worth. Independent measurements have since shown that in terms of performance, Galileo is the best operating positioning system in the world.
On the 15th of December 2016, the Commission announced initial services. This was an important moment because this was the first time that we formally announced that there was a certain service available with a certain quality for a certain time of the day. Since then, we have been building out the constellation, and it has been improving every day. We now have independent measurements of the performance of the Galileo system, and it is actually, to be honest, and we are very proud of it, the best in class. We are having a better performance than our 3 competitors from the US, which is the well-known GPS system, the Russian GLONASS system, and the Chinese Baidu system. So, of course, in ESA we are excessively proud of this, and it is now important that we keep building on this performance and hopefully keep at the forefront of the developments.
But the work on Galileo is far from done. The European Commission and ESA are already working on the next generation of Galileo satellites and infrastructure. They aim to continuously improve the system and explore the boundaries of technological possibilities while trying to meet market demand with potential new applications or services.
The system will undergo continuous improvements. Obviously, the market is asking for that. The technology is ready for it. Every couple of years, there are new possibilities. And the combination between what the technology can offer and what the market is demanding leads then to decisions on how to improve the system so that we can provide further and more services. A number of areas, for example, which are coming is the so-called Internet of Things, which will require positioning in sensors. And these sensors have very little power and very little battery capacity, so we need special signals for that, probably. And in addition, another area which is of interest is autonomous driving, where satellite navigation is going to be a very important component, but where it needs to be integrated with all sorts of other sensors in cars in order to make sure that autonomous driving becomes a reality.
With more launches to complete the constellation and set up redundancies, Galileo's performance and availability worldwide will continue to improve gradually, keeping Galileo at the cutting edge of satellite positioning technology. Today, the only publicly owned satellite system has also proven to be the best.